ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು. ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು.
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ
A very good morning to one and all gathered here. Welcome to the second day of our FDP program, Deep Learning Techniques for Advancing Medical Image Processing. Today's distinguished speaker is Dr. Dinesh R. Dinesh R is a principal engineer at Samsung. Prior to joining Samsung, he worked for companies like Amazon, Honeywell, HCL, and he was a postdoctoral fellow at Seoul National University. His areas of research interest include image processing, pattern recognition, computer vision and machine learning. He has 60 plus publications at international and national journals and conferences. He also has 27 awarded patents to his credit. He is serving as the editorial board of several journals, reviewer of several international and national journals and conferences, technical program committee member for several conferences. He has successfully guided 3 PhD scholars and currently is guiding 6 PhD candidates. He is a life member of IEEE Application Computer Society of India, Society of Statistics, also advisory committee, BOS and BOE of various universities. Sir is Dinesh R. Dr. Dinesh R is very famous. You must be knowing him. You might have listened to his lecture. His name is there in almost all the brochures of international conferences or workshops. So he is a PhD scholar of Dr. D.S. Guru sir from Mysore University. Welcome you, sir. Over to you.
ಬರ್ತಾ ಇಲ್ಲ ಚೆಕ್ ಮಾಡಿ. Hello. Yeah. Good morning to all of you. Yeah, okay. So before I start, let me take the opportunity to thank Dr. Shekhar sir and Sujireka madam for giving me the opportunity to share my experience with you people. Okay, so and I want this session to be more interactive. So I have some slides, but don't go by that slide. Like it's quite old slide. So if you have any specific questions or anything, you try to open up. We will discuss, and then we will try to learn together. Okay, so that's what I want to. So hopefully, like. Most of you are all familiar with the terms, basic terms like, okay, so what is neural network, what is deep learning, and how to construct. Okay, we'll just try to brush it up. And this is what the agenda I wanted to cover in today's session. Like, okay, so we'll try to first quickly understand what is deep learning. I think most of you are already familiar. And let us try to understand or discuss about why deep learning. Okay, so why deep learning is important, or why deep learning is gaining so much of popularity in the recent times. And we will try to construct deep learning for images, so CNN. And so if you have any specific use case other than images, if you are working on any other data modality, let me know so that we will try to discuss more on that. We'll try to understand autoencoders, so mainly from the perspective of generative models, how to construct a generative model. Like, so these days we are talking about GPT models, right? Chat GPT or like so generative AI. So from that point of view, like we just wanted to touch upon autoencoders. Okay, so that's a basic building block for most of the generative model. And then finally, we will touch upon some object detection models which are available. Like, okay, so if you are working on a detectors, okay, how to construct that kind of detectors. And of course, I will, as part of the detectors, I will try to touch upon the deep segmentation models. Like, okay, so SAM, segment anything. And so towards the end, I just want to touch upon the type of work what we do in Samsung electromechanics, especially in the AI lab, and what kind of problem we are trying to solve. This is what I am trying to cover. As I already said, like, so don't go by this sequence or even the content. If you have any specific topics or any thing that need to be discussed, please feel free to open up so that we can discuss and we will try to learn. Okay? Yeah, with this backdrop, like, let us try to start. I think this all of you are familiar, right? Like, so what is machine learning? So that's where we start with. I think probably, I think you discussed yesterday also, I think probably, see, mainly like, okay, so yeah, you want like, okay, so whatever the learning we generally try to do as part of like, okay, so our day-to-day life, we expect machines to perform the similar kind of task. Like, I don't want the machines to execute whatever the program written, rather than it has to learn through the data, learn through the instances which it encounters. So typically, like, okay, if you look into the machine learning, you have like, okay, so a training phase and a testing phase, or the inferencing phase. So a lot of labeled data, and you try to build a machine learning algorithm and use that whatever the model you built. So if you give a unlabeled data, so it's not a labeled data, unlabeled data, like, okay, so how you are going to utilize this the model to do the prediction. So that's what generally we try to do it. Actually, basically, I have some instances of data. Using that data, we try to learn or build a model. And once the model is built, so we generally give unlabeled data. It's not a unlabeled data. And utilizing the learned model, I want to do the prediction. Okay, so at the nutshell, this is what generally we try to do it in machine learning. Okay, so I think again you are familiar with different type of machine learning, like supervised, unsupervised, and reinforcement learning. These are the three categories. If you take any machine learning algorithms, they can broadly be classified into one of these three categories. Okay, a supervised learning is a one where you have a labeled data. That means for every instance, whatever, when you are building a model, you have a labeled data. Using that labeled data, you try to build a model. Like, so that is a supervised actually. So this is what like, okay, so most popular and widely used approach for machine learning. But unfortunately, it has a limitation. See, nowadays, if you look into, see why we started with supervised learning when the machine learning was started, right? Like, so we were talking about mostly we were talking about the supervised learning. At that point of time, like, okay, so the data generation was not that great actually. Like, so the data generation was not that rapid. But these days, if you look into the scenarios, you look into the amount of sensors mounted on the machines, or like, okay, so the amount of data being generated is enormous. Now the question is, if the data is generated at such a rapid speed, how you are going to build a model? See, I cannot employ a supervised model because, see, if I take an example of our own company, Samsung, see, we have factories around the world, and factories works like 24/7. Now the question is, if at all I want to generate a data generation is not a difficult task. I can keep on generating the data because, like, okay, even if I collect 1 day's data from all over the world, like, so probably we will be generating some terabytes of data, including images and different type of data. Now the question is, can I straight away use this data for building the model? So I cannot go for a supervised model because somebody has to curate this data, like somebody has to prepare this data for the machine learning task. So in terms of generating the label. Now, generating such labels itself is a very, very cumbersome and difficult task. In such scenario, how you are going to utilize, how you are going to consume that kind of data for building the machine learning system. Okay, so that's where, like, so it give rise to unsupervised models. So nowadays, most of the companies are interested in utilizing this type of models actually, or this kind of approach, where data is available, labels are not widely available. So now utilizing this, how best I can build a model. So that's what, like, we saw unsupervised model talks about actually. I think probably, like, you are familiar with the data clustering and, like, so the grouping approaches to generate these models using unsupervised approach. So again, like, okay, so there are variants of unsupervised or a semi-supervised models we generally call. So where some amount of labels are available. Okay, so typically, like, okay, so if I take a population of the training data I have, so probably, like, okay, so 1 or 2% of the population may be having, like, the labels. Utilizing that, how best I can extend the labels to other data available. So that's what, like, so semi-supervised learning models. So where, like, so we try to utilize some amount of data, whatever labels are available, how best I can extend the labels to other similar data. Anybody is working on these kind of approaches, like, okay, so the unsupervised, like, the problems where you are having a data and, like, so you don't have the labels and you want to extend it. Okay, so that's what, like, so generally, like, so the clustering is one popular approach. And another category of learning is a reinforcement model, so which mainly works based on the feedback or the reward system. Now, how do I make system to continuously learn or continuously upgrade? Okay, so that's where, like, so these kind of feedback or the reward system behaves in a, or the training of these kind of systems are slightly different, where whenever the model is performing, say I know, like, okay, so there is a final goal. Okay, so to reach that final goal, there is an intermediate stage. And whenever, like, okay, so it makes the move, like, okay, so it takes the intermediate solution, you try to see whether that intermediate solution is appropriate to reach the final goal. If that is the case, you try to reward. If it is deviating from the goal, so then you penalize. So based on that reverse penalized model or the feedback model, you try to learn a set of rules to reach the final goal, so that, like, so your global optimal or, like, global objective is always met. Okay, so those kind of systems are called reinforcement learning. Probably we'll try to study in detail, like, so, or, like, so a few case studies at the later stage. Any questions so far? See, in all these cases, so typically like, okay, if you look into the traditional machine learning, right? So why like, the machine learning is not new. I think most of you are already familiar. So though machine learning is having like, so 50 or 60 years of, but only like, okay, so machine learning or like, so the artificial intelligence come into forefront only in the recent age, at least like in the mass. Okay, what was the main reason or what was the main problem with the traditional machine learning techniques? Okay, so the main problem with the traditional machine learning technique was, one of the thing is like, so you need to have a large amount of data. So probably like if at all you want to build a successful machine learning or like so scalable machine learning models, what are the challenges or what are the blockers probably like, so you need to have an enormous amount of data, one, and then for every data you should have a labels. Okay. How do you do the labeling? So it requires like a lot of domain expertise. Then you need to describe that data, like so whatever the data you are having, you cannot straight away use it as it is. So somehow you need to represent those data in terms of its representative features. Okay, so that feature engineering was one of the major tasks actually. Like even if I give a data like image, you cannot straight away use those images as it is. In the traditional machine learning, you need to extract certain set of features, which again, how do you decide what kind of features you need to extract? That is again like so defined by what kind of problem you are solving, and so it requires a lot of domain expertise. All these things only like, okay, so we'll try to tell that, okay, so you need to extract these kind of features. Now, your problem of machine learning, like ultimately you want to train or you want machine to learn from the data, but in other words, you try to follow up like, okay, so extracting a certain set of features and then representing those data and then end up in building, training the model. So these kind of things made like, okay, so the traditional machine learning as a limited success, or like, okay, so not everyone was able to adopt or extend this machine learning because it's very, very subjective. Okay, so typically if a different person like, so they may try to extract different set of features, they may extract it in a different form. So because of those kind of challenges, the traditional machine learning has got its own limitations. So one of things is the domain expertise to decide what kind of features, how many features you need, when to extract, etc. and so forth. And computational complexity. So because like, okay, so you are spending additional time in terms of extracting the features and then like, okay, so training those model, the computational complexity at that point of time or the computational infrastructures available at that point of time was not able to support those kind of mass adoption. Okay, so that is another. And there was a gap between the feature extraction and the learning models. So I think probably this you can understand. So typically, in a traditional machine learning technique, what are the steps you follow, or what is the pipeline of traditional machine learning? You have a data. So then you acquire the data. So then pre-process the data. Then you extract the features. Then you do the feature selection, and then you build depending on your approach, like final objective, either you go for grouping or like with a classifier. Now, you extracted certain set of features and you selected some classifier. So classifier doesn't know like so who extracted the feature and for what purpose the features were extracted. Getting me right? So what is the final objective? Final objective is like I give some certain set of data, I want to learn and I want to do my end objective. In this process, so you perform the pre-processing, you extracted the features, okay, and feature extraction and your classifier doesn't talk to each other. Okay, there is a gap. Okay, pre-processing and your feature extractor doesn't know like, okay, so each other like, so there is a gap. So this is called like, okay, so we generally call it as a gap between the data. So that means when you try to prepare the data for the end-to-end objective, so each step is driven by the expert. In this case, the machine learning or like so whoever is the domain expert, like so he is deciding like so, okay, I will use this classifier, I will extract these kind of features. Everything is driven by this person. right? And again, the domain expertise like so varies between the type of data you are handling. For example, if you are handling a medical data, so definitely you are a machine learning engineer or a data scientist or a computational engineer, but you are not an expert in the medical domain. So you need to rely on the expertise of the doctor or the physician to get to the insight. And you need to understand, and then based on that, okay, you need to decide, oh, okay, he is telling, okay, so this is a, if you are doing a brain image segmentation, oh, this is a gray matter or this is a white matter, and I need to, this is how it looks. And based on that, you need to decide, okay, so these kind of features I may extract. So, and again, there is no guarantee that whatever the feature you are extracting is a appropriate one or not. Again, you need to go back and, so all these things, gaps, okay, is a major blocker in extending the solution or making the solution more generic in nature. So, what is the end objective? I want my model to be more generic in nature. When do you say your model is generalized? It should be able to like, okay, so I have a representative data, it should be able to learn and it should be able to work on a bigger population of data. So then I say it is generalized, but there is a lot of gap to achieve that generalization. Because of that, so there was a limitation, and so though machine learning was like, okay, so having a limited success in a small scale, like, okay, so or in a small pockets of problem solving, but it has its own limitation in extending it for a wider or a bigger applications. Clear? Any questions? Less data? Mm. Right. Yeah, so that is another discussion. Like now the question is whether you need more data or less data actually. See, now the question is more than a number of the amount of data. Like so generally we even in case of a deep learning or even in case of a machine learning, right? So when we talk about the quantum of the data, so it's always the quality of data is more important than the quantum of the data. See, for example, there is no point in having like so maybe like millions of samples with smaller variations. See, I am trying to solve like, okay, so for example, like you are building a OCR, let us say, okay, handwritten, and if you collect only the numerals, so 0 or like, okay, so 1 from a limited users, or a, one particular geography of users. So then there is like, okay, so the variations are very, very less. But my objective is what? I want to make it more generic and it should work for all cases. Okay. So collecting 1 million of million data sample from a small group of people may not help actually. Okay. So even whether it is in case of a deep learning or in case of a machine learning, we always want data which is a representative of a bigger population. So it's all about a like bigger population, right? So now how you are going to sample those data for your training? That is what is very, very important. So if you don't sample the data, if your data is not spread across, see, when I say this is what I meant actually. See, let us say this is the bigger population. This is the entire population of the data which you want to work, your model has to work. See now, I cannot train my model on the entire data, this population. It's either, it's not that, okay, I am not able to train. So it is not possible to collect all possible data. Okay. So now, what you try to do, you try to do some population of data, right? You try to like, okay, you try to do the sampling of this data. Now, how you are going to sample this data? That is what is more important. Like, for example, if you sample all your data, let us say like this is the case. Okay, this is a bigger population. This is what my training data. But unfortunately, you sampled all your data from this case. This may not represent the other part of the data. Okay. So even in the case where like, okay, my data is, the number of samples are same, But if it is not spread across your sampled, your population, then like the quantum of data doesn't address your problem always. Okay, always ensure that whatever the data you are trying to get for your training models is always spread across. Like so, you collect it from a different population, spread across. Yes. Hmm.
That also will become a complicated thing. We want to classify many more number of data than the required one.
Yeah.
And the required amount of data, if you are over sampling or over sizing, that also will be making the system complicated. No?
Correct. So basically, like okay, so if you end up collecting like okay, so the question was like okay, so if I increase the number of training samples in my training process, don't it make the system complex? Okay, so it may not make the system complex, but it may take more time to train. Okay, in this process, there could be other things can happen like so it can get into different problems of the deep learning. We will try to talk about those things. Now the question is, of course, more samples or more data you are having, it may take more time to converge or more time to build the model, or it requires more computational effort. At the same time, is it possible to like, okay, so now how are you going to decide whether that whatever the samples I am having is sufficient or not? Okay, one is that, and so am I having data which is it may not be adding too much of value, but I am just collected too much of samples. How we are going to handle it actually? So that is like okay. So there are very interesting approaches to solve this problem. Like okay, so let me just give the glimpse there. See now, like for this one. So generally, like okay, so one of the approach like okay, so we try to build in. We have the same kind of problem. Okay, let me give like okay, so what is the problem like? So we manufacture MLCC chips. So these MLCC chips will be part of various electronic devices, including automotive, your electric vehicles. Now the question is, when we build this, when we manufacture this chip, okay, there are multiple tests we try to do. One of the tests is visual inspection. We try to do the visual inspection, where we try to, in the afternoon I will show the system how it looks like. So typically like, so these chips, like if you hold the chip in your hand, it may contain like billions of chips. It's so tiny chip actually. Okay. Now the question is like, so these chips has to be inspected in a real time, as and when it is manufactured. And so chip looks like it's a rectangular thing like, okay, so it's a, typically it looks like this. So the scaled up portion is, so MLCC chip, probably if, some of your from electronics background, probably you might have seen that multi-layer ceramic capacitance. Okay, it's a capacitor chip. So no, it just like, okay, looks like a rectangular thing. So this has to be inspected from all the sides. When we try to do the inspection, we try to see like, so whether there is any visual defects, okay, inside that from the chip. That's what we try to detect. Now the question is, if I manufacture, if I start collecting the data, any factory, when we are trying to manufacture, like so mostly like 98% or 99% of the time, it should be okay chip, and maybe 1 or 2% of the time, it can be a defective chip. So that's what like, so there is no point in continuing the manufacturing if it is having more than 10% or 12% of defects. So that is quite common for most of the cases, right? Even if you go to medical, if you start collecting the medical data. So there is a high guarantee that, okay, so the normal cases, right? For example, if you try to collect the data from pathological, from a lab. So if in a lab, in a day, if they test maybe like 100 people, how many people like, okay, so it can be a normal case, and how many instances it could be a, what is that, positive or like, so the abnormal cases. So typically like, okay, so even generally we expect like, so maybe less than 10% is the abnormal case, and most of the time it should be a normal case. Clear? So this is the quite natural phenomena in most of the case. And this is the most challenging problem that we need to address. Okay, even when we are trying to solve the problem or the data collection problem, right? This is the most difficult challenge or the most important aspect that need to be solved as part of the data collection. In any case, okay, so you take banking application. Okay, so most of the transaction is expected to be a normal transaction, maybe like, okay, so less than 1 or 2% is expected to be fraudulent transactions in a day. Clear? So now, what is important? What is important? What is the, when you are trying to build a system for banking application or even for the medical case, what is the problem? Your problem is not to identify a normal case, to identify the abnormal case. But the amount of data you get for the abnormal case is very less. How we are going to handle this? That means when you try to take this population, right? So you get a bigger population, bigger data for normal case, which is not of my interest. My interest is opposite of that. How we are going to model your system? Okay, if you want to collect that equal number of samples, okay, see, let us say like, okay, here you collected 1 million samples. So if you want to collect 1 million defective samples, how long you need to wait? Okay, and again, here like, so when we talk about the MLCC case, right? So this is the practical problem what we are facing. Okay, and then, so in the MLCC case, in the MLCC part, so we have about 20 different type of defects. That means whenever it says defect, so there could be 20 different categories. My objective is not only identifying whether it is a defect or not. My objective is also to classify what type of defect it is. Whether the defect is in the electrode part, whether it is a defect in the body part, whether if it is electrode, whether it is a chipping, or whether it is protrusion. Those kind of defects I need to identify. Now, collecting the data for all defects to make it balanced data set, it becomes practically impossible. How these problems will be handled actually?
As a class belongs to healthy, means without healthy class, otherwise is not healthy class, it will be comes under.
So one of the simplest way of solving the problem could be like, okay, so it's instead of making the problem, like, so this is where like, okay, you need to decide whether you are going to make it as a classification problem or a anomaly detection problem. First, categorize, okay, so whenever there is a abnormality, right, so you classify this as an anomaly. Rather than taking like huge sample of OK class and then like, so a small sample of NG class. What happens like, okay, so if you try to take 1 million OK chips and maybe like, okay, so thousands of defective chips, so obviously your model will not be able to learn. But this is what I am trying to convey to your problem. See now, my data for the normal class is so big and for abnormal cases very small. And when you try to allow the model to learn, obviously it will try to learn that OK classes rather than the defective class. So now if you try to train your with this kind of data, if you try to train a classifier, obviously you are going to fail. Rather than that, you try to define a abnormally detection, anomaly detection. Okay, this is what my normal data looks like. Anything which deviates from this normal case, I will classify it as an anomaly. Now it will trigger, okay, there is an anomaly with this. Now you go back and try to build a classifier, smaller classifier to see what type of defect it is. Now I am no longer I am trying to train my system with the normal data, rather than I am trying to train with only abnormal data. So that way you can try to avoid collecting these kind of data. Clear? So always you should, when you are trying to build a system, these are the factors you need to consider actually. What you are trying to solve. See, this is what like, so even if you look into the banking application or the transactions, right, they don't try to classify it as a classifier problem. They always try to see like, so whether it's an anomaly or not. or whether it's a suspicious transaction or not. If it is a suspicious transaction, then only they will try to see, so what kind of suspicion, like, so what kind of defect it could be.
50% normal data, 50% abnormal data and all.
Madam,
In such case,
see,
some of the students are doing like that. That is why I am asking.
see, those are all like, okay, so the traditional textbook way of telling, like, okay, so you need to make it balanced.
Yes,
You should
of
have like,
course.
okay, so 60%, so probably like, okay, so 60% for training. And again, that 60% of data, if I am trying to having two class problem, your data should be balanced and all those things. But when you get into the practical problem, this is one problem I explained, right? You take, see, if you talk about the data collection problem, for most of the practical problems, so this is the case. You take medical application. If you go to hospital and you ask for like, so if you search for 1 month data, there is a high chance that, okay, 90% of them are normal and 10% only like abnormality. If you go to bank and you collect like, so 2 months transaction, 90% or 95% or 98% of the time, it's a normal transaction, only 1 or 2% is an abnormal transaction. Even if you go to manufacturing industry, even if you take a produce grading, you harvested the fruit and you are trying to grade it. So there also like, so most of the time it is a normal produce, only like, okay, so few cases a defect or like, so abnormality. Any problem you take, in reality, if you want to build a system, so most of the things will follow this pattern. Now, you will be in a fix if you go for a traditional classifier, assuming that, okay, I will collect the data. How long you will collect? For example, if you are working on a food grading, so you have only one harvest actually, like, and if you want to collect like some more data for a defect, you need to wait for 1 more year. Is it practical? So it's not practical. Like. So now, how you are going to tune your model? So that's what is more important. Okay, always keep it in mind. See, when you are trying to do academic research and you are trying to have a sufficient data, your hypothesis is fine. But when it practically you want to solve the problem, the situation and the scenarios will be different. You try to always take that into account.
Another basic doubt, sir. For training, we take some kind of data. For doing the testing, same type of data must not be used, they say. For testing, we have to say, for example, 100% data is available with us. 80% data is taken for training, and the remaining 20% data taken for testing. Is it correct one or?
See, basically, why? Okay, so there is a twofold answer for this. One is you have sufficient data, and that data, like, so whatever the data you collected, and so that 20% of the data, whatever you are telling, so why we are telling that one is, so for that 20% of samples, the labels are available. I am just trying to utilize that to confirm whether my model is working or not. Okay, that's all. But the moment I deploy it into a system, operations, so probably in the afternoon we will talk about the ML ops actually. Like, so this is another very interesting thing. So now I deploy the model. How do I say my model is working fine or not? Okay, so this is very interesting problem, like, okay, many companies are solving, like, so ML operation, like, so DevOps, whatever generally we try to do in the traditional software development, right? How do you ensure that, okay, so your machine learning model in the operation has to be maintained? Okay, so now coming to your question, why we use like, okay, so that 60%, 40% or 70%, 30% split is, so I have some data set. I have collected like, so let us say 25,000 data samples. That's the data sample which I have like for building my model. Now what I will try to do, so I will try to take 70% of the data or 60% of the data, and remaining 30% or 25% of data, still I have a label. What I will try to, I will not show it to my model while building that model. I will try to train my model using this 60% or 70% of data and utilize that remaining data, whatever that 40% or 30%, to confirm that, okay, my model is working fine or not. That's it. But there is no guarantee that you confirmed, okay, yes, with this 30% of my test data, it is giving 99%, okay, let me use it. And there is no guarantee that, okay, so this your 30% of data, whatever you used, confirmed. So we'll have like the same kind of performance when you put it into the operations. How do you see like, okay, so for example, you are building for autonomous driving. You are building a model for autonomous driving. What is your objective? So from a leading image, like so from the camera, whatever the camera mounted on your vehicle, when you try to detect an object, you need to classify what kind of object it is, and you need to estimate a distance between your host vehicle and the leading vehicle, detected vehicle. So you use like all-over model, and like so it gives like so 99% accuracy. In 99% accurately detect the objects and measure the distance. Now there is all of a sudden new kind of truck came actually. Your model is not able to detect actually. How you are going to ensure that? Okay. Now I have put model in the operation. How do you ensure that okay your model is still able to? Okay, so but okay, that mean average precision is computed based on your test data. But how do you say like for that data, the incoming data you don't have a ground truth. It's completely unseen and you don't have a label. How you are going to say that okay your model is performing well or not? So you got it right. Say for example, if you are building a OCR, see these are the data samples you are having. So for this, you have a label, and if your model says it's a 0, yes, it's proper. So if it says 0, okay, it's not proper. So this is how like you try to say like so what is your mean average precision, or like say you can compute a confusion matrix when you have a ground truth for your test data. Now I put it in the operation. In the operation, it's only incoming data, like okay, so nobody has seen that, unless like okay, some expert sees that okay, oh, it was supposed to be identified as 0, but it is detecting as a 1. How you are going to say like okay, so your model is still performing well? Think about the challenge now. Now, in a factory or like in a system, you put the model. What is this model? This model has been tested on my ground truth, and it is working 99% or 100%, let us say. So because of this, I put the model into operation. Now it is working. 1 month over, 2 months over. How do I ensure my model, even after 2 months or 3 months or 2 years of operation, it is still giving 99% or 90%? Okay, how are you going to update it? Okay, what is your trigger point to update the model? Who will take that new sample? So this is where like so MLOps comes into picture. So now I put the model in the operation. Nobody is there to guide it. Now there are multiple things need to be taken into account. When to collect the data, what data has to be collected, when to trigger the operation, when to trigger the updation. Of course, like so nowadays we talk about the transfer learning, everything is fine. But when do I trigger the transfer learning? Transfer learning on what? Should I collect all the data and do the transfer learning? If model is working fine, I should not do it. Then I need to collect only sufficient data or like so necessary data to do the transfer learning. Okay, which data has to be collected? How do I decide, okay, so this data is sufficient to perform the transfer learning? Okay, now I have this model, base model MB. I have a new model MN. How do I decide? Okay, this MN model will replace this, the base model. This will become a base model. And how do you automatically deploy it? Getting the problem? So these are the problems, these are the kind of problems, like okay, so the people who are involved in the MLOps, right? So they are working. So how do I decide, okay, whether your data is drift? How do I decide the drift? There is a drift. What measures has to be decided? What parameters you will consider to decide the drift? Okay, so very interesting problem, right? Like so, see now, for example, one of the simple thing is, see, this is my training data, has got this kind of distribution. So now, whenever I put it into the operation, over a period of time, data is drifted like this. My model has learned this distribution, but Last 2 months, I am seeing there is a drift in the distribution. So this is what we call it as a data drift. Okay, this is data drift. That means my input itself is drifting. Okay, this could be one trigger point for collecting the data. So then we talk about the model drift. Your model is drifting. So how do you handle this? Okay, so these are the kind of thing like we need to talk about in the case of MLOps. Okay. So MLOps is a part of like, see, it's a bigger system actually. Basically like, okay, you need to have a mechanism. It has multiple things. It requires infra. What type of infra it is? Like, so how do you collect the data? See, basically like, if I talk about the MLOps system, right? So typically what happens, I think all of you are able to see this color pen, right? See now, your, we call it as an experiment. What is this experiment? Experiment is the place where you are trying to build a model, okay? Where you have like some training data set. So this you try to split it into train and test, or you try to do the cross validation, whatever it is. So now, with this, I build a model, M. This model has been tested with test data, and this confirms it is a base model. Now, somehow I decided, okay, this model is meeting my KPI. Okay, so that means like, okay, every organization, every data scientist will be given with some KPI. Okay, key parameter that need to be satisfied. So with that, so it is meeting the KPIs. So now this model has been called as a base model. So when I say base model, like, okay, so this model is ready for deployment. So now this model, this is your lab infrastructure. Okay, so with this lab infrastructure, you build the model, and this model now will go for deployment. So you will put it into the deployment server, and this model will be in the deployment server, and it will be called by inference service. So this inference service is getting the data from the actual manufacturing site, and it will refer this data and try to give the inferencing. Now, this inference result has to be stored somewhere. Why this has to be stored somewhere? We don't know, like, okay, so it's only inference result. I don't know, like, okay, whether it is a OK, NG, nobody knows, like, so what kind of it. So now, look at the challenge here. When I am trying to use this inferencing system, like, so the base model for the inferencing server, so this is working in a real time. See, for example, if you are working in like detecting a fire and smoke, it has to work in a real time, like so with 30 frames per second or 20 frames per second or whatever this. So here, speed is very critical. Your inferencing server is how fast I can do the inferencing is what is very, very important. So that is what one of the KPI. Now at the same time, somewhere I need to store this result, and this inference result doesn't have a ground truth. Always remember, like it's a new data, it's completely unseen data. Now it is a, now when you are going to run, when you are going to monitor this is something has to be monitored, right? Monitor for what? For what purpose you need to monitor? To monitor, is there is any drift in the data? Is there is any drift in the model performance? So based on that, you need to decide. And this monitoring should be, most of the time it will be a routine services, or it will be running in a different server. Because if I try to run the same thing in the same inference server, so it may like choke, or like it may reduce the performance of the system. So typically this will, at least okay, in Samsung what we try to do is, we try to run this as a scheduled service. It will be scheduled to run every day midnight, where, so we have a lesser load on the network bandwidth, and So the lesser node on the servers. Okay. At that time, we try to run this, and we try to monitor data drift. So mainly for data drift, we try to utilize the distributions to see whether it is your data, whatever the data collected in the last 24 hours is deviating in the distribution from the original distribution. And model drift. So what is model drift? How do you measure the model drift? I think all of you are able to understand what is data drift, right? Data drift is, so when I train, like so in my training data set, where do you get that? So in this training data set, if I try to plot the distribution, maybe like so this kind of distribution. For this distribution, I know the statistics, and I try to compare. So this data, is there is any like matching within the distribution, or it is going outside the distribution? How do you, what do you mean by model drift? How do you say that model for? But how do you know like it's 99% or even 10%? I don't know the ground truth. Getting the point, right? Because it's last 24 hours data. This data doesn't have a ground truth, and it was not, of course, not seen. What could be the model? What could be your thought about model drift? So model drift is this. See, I take a data in the same distribution. Yesterday, it gave this result. Today, for the same data, it is giving different result, R2. That means, for a same distribution, model is drifting. Okay? So, this is also very, very difficult problem actually. So, that means, over a period of time, like, so your model is slightly moving away or drifting. Okay? So, this also need to be addressed. So, we try to see like, okay, so there is, okay, this particular data, okay, whatever the data stored in this 24 hours. So, these are the samples outside my distribution. Then you trigger, okay, collect this data. That means don't collect any data which is within the distribution because already trained. You need not to collect that. Okay? I try to collect only the data which is outside my distribution. Now I try to also collect the data where why this drift can happen for the model drift. Data drift, it is clear. Why model drift happens? Because these are the samples. When I train, okay, if this is my decision boundary, okay, data here, no problem. Whichever the data which is in my near to my decision boundaries or which is less in quantity. So this is actually causing the problem. That means in my training data set, whatever the previously trained data set, there is no sufficient support for this data. I need to have more number of those kind of data. You try to collect those two. Once you have like, okay, so then you have a policy like, okay, so now I will try to perform a transfer learning only when sufficient amount of images is available. So not like every 10 images. Maybe like, okay, you can decide. If I have like, so 5,000 images available, I try to trigger. Then you trigger the transfer learning with this data. Now you get MN, the new model. Now you try to compare this new model with the base model for what? Again, for your confusion matrix and everything, to see whether this newly constructed model is good enough, not only for the newly get data, but also for the previous data also. If that is the case, deploy it, otherwise don't deploy it. Get it right? So this is what, okay, so of course, like, so this will be like, you will get a MN, so you will have a model comparison. So all this automated system. So then, so you will have like, okay, so the new metrics available, and based on this metric, you can either put this to inference and this replace this, or not to replace that. Yes. Which one? Yes, of course. Like, okay, so these data will be like, okay, so, okay, now you got this new label, new samples, right? So now either you have two options. One is you collect this, whatever the samples collected, you either give it for expert to label, or it's not required. Generally, we don't do that because already I know, like, okay, so the sample data. Using that data, I will try to generate a pseudo labels. So generally we collect as pseudo labels, and I will give like, okay, so these are the data I collected, these are my pseudo generated labels, you confirm it. That means the operator need not to relabel it, just verify it, like, so whether the labels are proper or not. Because if I give like, okay, so again labeling, so it's a cumbersome task, right? Ultimately, my object is what? My object is to remove the human dependency at all. If there is a human dependency, I need to remove it. So generally, we are trying to do the pseudo labeling. So now, again, this is a machine learning algorithm. Then it comes its own cycle. So once everything is converged, that entire system will be in the fully automated mode. Without any human intervention, the system can run for years. Getting? So where like, so the academic research, so I am not telling that, okay, academic research is bad. So academic research is like, we generally don't take care of these things. So when I say academic research, even including our, when we try to build a model, we try to focus only on this. But when it goes to operation, it has got its own challenges. Clear? See, when you do the transfer learning, you are trying to do the transfer learning on like, so previously available weights on the newly collected data. So now, if you want to double ensure, like, so try to add some samples from. No, so generally like, okay, so at least, okay, so now if you try to take only the negative samples here, NG cases, so then the data is not balanced, right? To balance this, you should have sufficient OK cases also. Both will be added, and because this is the basic problem, right? Basically, when you try to do the transfer learning or the first fresh learning, your data has to be balanced. To balance it, we will try to balance both. So now, okay, so now this model will have like, okay, so this distribution, and ideally like, okay, so this MN, the model new is turning out to be a base model. Ideally, this should learn both the distribution. Okay, madam has raised very interesting problem. Now think about a case. I deployed it for like, so it is working for 2 years now. What happens like, so if your distribution is like, what could be the problem? So that means every 3 months it is shifting. So now every time I try to update my model, like, okay, so now your model is learned such a bigger distribution. Is it relevant now? So over a period of time, it may become less, almost like so big. It doesn't learn anything, right? So it may try to tend to classify everything into one class. How you are going to handle this? So you tend to overfit. How to handle this? Keeping earliest data or keeping removing the earliest data? Keeping the newest data. See, again, that need to be supported by your business. See, for example, if I am in a factory or any manufacturing, I am trying to manufacture new type of model. So because of that, there could be a distribution change, or there is a like, okay, so different type of the process has been followed, or my raw material is different. So because of that, distribution might have changed. You need to decide like, so whether in the future, if you are going to get only these kind of data or the raw material, So then there is no point in keeping this, to trim that actually. So that means when you try to do the retraining, you ensure that, okay, so these kind of data I am not going to encounter in the future. For example, see all these days, like so in the Samsung, like we are manufacturing the PCB for, let us say like, so still we are supporting S22, S21, S23 and S24 of course. If I am not manufacturing, if I have decided that, okay, I am not going to manufacture like, okay, so S10 or S9, there is no point in keeping those kind of, you can just try to trim it. So that way you can, rather than adopting this kind of distribution, just try to shift, keeping like, so whatever the data you are going to support. Okay. Any other questions? Okay. So in that case, yes. So this is not generally applicable for all cases. Okay. So now how are you going to handle this case in case of medical? Either you try to segregate. Okay. So okay, these are the different categories of disease. For example, if I try to take it from a specific medical device, a diagnostic device. So now I will try to segregate. Like so, for example, this is from a specific vendor like so Philips, and this is the data coming from GE. So probably I will try to segregate based on that distribution or based on the geography. Like that you need to decide. So always ensure, see ultimately what is more important, always try to keep focus on your final objective, end objective. Okay. If your end objective, if you try to dilute, then there is no point in building this solution. So with respect to your end objective, what is more relevant and what is more appropriate, that you need to always take into account. Right. So these are the challenges, and like this is how the deep learning is formed. I think probably this also you already learned. Like so, basically, we try to bridge the gap between the feature extraction and the classification. Okay. Or like so, to overcome the burden of handcrafted feature or the manual feature extraction, we try to build a deeper models to learn the features and train the classifier. That way, so this classifier will extract request for the feature which are suitable for the classification purpose, and this feature extractor will extract those features which is more relevant for the classification purpose. Clear? So this is what I think probably like the same thing. So this is what like so the traditional machine learning, okay, where like so we try to describe your data with the features which can understand, and then there is a learning algorithm. These two things are put together in case of a deep learning. Deep learning is, so not only like okay, so having a deeper number of layers, we will try to understand what is that, why it is called deep learning and other things. Mainly like okay, so there is a feature learning. Okay, so the feature extractor and then performing a classification put together. That's why it is a deep learning. Okay, so the feature extraction will not be explicit, like so it becomes implicit part of it. So where like you try to learn the features and train the predictors. So I'm not getting into the detail. If you need any details, let me know so that we'll discuss. Otherwise, I think probably it is already covered. I am just trying to skip those parts. How do you interpret this graph? So my x-axis is the size of data, y-axis is performance. As the size of data increases, so deep learning is expected to work better on the large data set. Is it guaranteed? Why it is not guaranteed? So same, I think we discussed about, right? So I have a bigger population, so it all depends on whether your samples, whatever you have collected the samples, is a representative of your population. If the samples are not representative of your population, then like okay, so having more number of data doesn't make any sense. Okay. Now like okay, so the question is, okay, So with the true. Now we are working. We are talking about that one actually. Like how do you make your algorithm to work on a lesser number of data? Like for example, again like so we are building system for edge computer on the go learning. So I want to deploy some model in the phone. So not only like so the inference model but training model also. Now how do you make your model? Because I cannot collect huge amount of data and try to train in a limited computational resources. Okay. How are you going to make that kind of system like? So now you need to filter out lot of data. So how are you going to do that? So try to reject the data which is again like with the similar. Okay. For example, like if you are having a 10,000 samples, now look or try to see that all these 10,000 samples are meaningfully contributing to your training process. If two samples are like so, some samples are similar, exactly similar, or like so similar in terms of their distributions, so then there is no point in keeping all the data points. So try to reduce those kind of things. Okay. So that is those kind of see when you don't have a you need not to worry about the computational resources, right? So large data makes sense, but especially when we are trying to handle or when we are trying to build a learning systems with limited resources or handheld devices, so then probably you need to take care of the quantum of data also. Okay. So in such cases, we don't only like talk about the quantum of data, so we talk about the quality of data. So whether your quality of data, that the data what you are trying to consider is a true representative of your population or not.
How to select that particular data is relevant?
One simple case could be, madam, like you try to group the data and try to see whether like okay, so the distribution or like so the spread of data, like for example, if it forms too many samples or cluster into one narrow case, so then like so no need to keep all the samples in that group. Actually, you can probably take a few samples from that actually. So that way you can start rejecting some samples which are almost identically similar with respect to the distribution. So identically similar, don't see that okay, so two feature rows are exactly similar. That is probably it is very difficult to find. So with respect to the distribution, whether they are identically similar, that's how we need to try to see. Okay, with respect to the distributions, because ultimately what you are trying to learn with your deep learning model, basically you are trying to learn the distribution of the data. So with respect to that, you try to see like so whether those data are appropriate or not. Okay, so that's why we can try to. There are a lot of statistical tests to see that okay, so whether that data is identically similar to the distribution. Using those approaches, you can try to filter out some of the data. Yes. So you can implement those kind of the tests to see whether this data can be a part of your distribution or not. So based on that, you can try to. If it is part of distribution, you remove it. Actually, you try to take, oversample. If it is not part of the distribution, so then you try to undersample. So, sorry, reverse. So when you like, okay, so for example, if you are having too many data coming from this, my data are like so from the three distributions. Okay. Now, if most of the data is in this distribution, you try to oversample. Like okay, so you try to collect few number of samples. Like so, even though there is like 10,000 samples in this group, okay, you try to take maybe like 100 samples from this. Okay, this group may be having like okay, so maybe only 200 samples. You try to oversample here. You try to take more number of samples. That way, when you try to take the data, so it is having a uniform distribution. Like so, you are trying to not only select, you are trying to select the data such a way that so they form the natural representative of the entire population, rather than like so uniformly selecting like 100 samples from every case or a 200 sample from every case or 10% from every distribution. You try to split it across. See, if you don't, see, if you implement, like there are many, I think probably, if you, there are tools already available. So there is a feast, okay, so which will decide, which will help you in, of course, you can configure this feast system where you can configure what kind of test has to be done. So once that is done, this will try to help you to select the features actually, like we said, it will try to store the features which are relevant. I think these are the part of like, okay, so your bigger MLOps system, because when we try to do the MLOps system, right, you need to not only select like, so some kind of samples which are very, very similar. So with respect to that, so feast is one tool, there are many such tools are available. So in Samsung, we generally use feast to select those kind of data samples. So feast stands for feature store, so which will automatically store what kind of features are more relevant for your subsequent transfer learning. Okay. Any more thoughts on this graph? Of course, like so more samples, so your deep learning performance will improve, and whereas traditional machine learning, okay, why the performance of traditional machine learning is saturating even if I increase the number of samples? Okay. Okay. So this is because of your feature extraction, because you extracted certain features. Okay. So now you extracted, let us say, color feature or some kind of features. So now increasing the data may not significantly improve the performance because it is already restricted by the features. How did you decide the feature? Based on your understanding. Okay. So there is no further augmentation possible unless you try to change your feature extraction mechanism or try to incorporate or increase the scope of the feature extraction mechanism. So because of that, so there is slight increase. So more or less like with the performance become saturated. Whereas in case of deep learning, you are not deciding, like so you are not fixing your feature extraction, like you are allowing it to learn based on the data. So as of course, like so the more and more data you are trying to add, so more possibly like you are trying to collect more number of samples from a different part of the population, because of that performance can increase. Okay. Now what, so for all this data, you already know like, so what is your labels? Okay. So you are not fixing this feature extraction, right? So this is free, like so basically you are trying to extract very, very low level feature. Probably we will try to see like, so when we start talking about the convolution. So if you are in a convolution, basically you are trying to extract like so very low level features from the pixel level to like so. Now nothing is fixed here. As and when the new data comes, so it will try to, based on the classification, like so it will try to refine this. Okay, that way it is open to learn. Okay. How it will extract? Like for example, you extracted 50 or 60 features, right? So that means whenever the data is, you obtain a data, irrespective of the data, you extract this only 60 or 50 or 60 features. That's it. And these 50 or 60 features, you try to give it for like so your classifier. So whatever the data, you are trying to look only for this 50 or 60 features. Okay. So there could be some variation within this 50 or 60 features. Because of that, there is a slight increase in this performance, but not drastic increase, because this 50 or 60 is fixed. Whatever the feature you extracted, right, that is fixed. Whereas in case of a deep learning, that is not fixed. Nothing is fixed. Right? So of course, like so nothing is fixed means that not everything is float. So of course you have a learning parameters what we talk about, but you have a sufficient number of learning parameters which can learn about these variations, and it will try to learn those features. Hence, this. Now the question is, when to use ML and when to use deep learning? Is machine learning is obsolete or completely you can forget about even talking about machine learning? Of course, like if you look into the taxonomy, like huh? Right. Deep learning works. Yeah, so we have that, yes sir, correct, okay. Hmm. Hmm. Yes, see basically like if you go back and like okay, so based on your newer understanding about data, if you rework on the features, again like so this graph need not be like the same graph, it may increase. But once you decide that this is fixed, once your feature extraction methods are fixed, so adding additional data may not significantly improve the performance in case of a traditional machine learning because you are confining the feature extractions because you are not allowed to learn. So only thing is within that feature, whatever the features you extracted, so based on that, like so you are trying to capture the variation, whatever the variations available in this within these features, whatever the features, it can improve the performance by that factor, but not significantly. See, the what is the thing is like so probably like you are driven by your analytics or you are trying to exploit your understanding about the data to derive this, and you are restricting at that point. There could be a lot of hidden meaning, so which will not be exploited with this approach. Okay, where in deep learning, so it is allowed to like nothing is fixed. So basically, you are trying to allow it to learn, and hence, so you are trying to learn that. That's how you try to define the performance. Now the question is when to select machine learning and when to select deep learning. Okay, then of course that is one case. Say for example, if somebody is working on a medical images, I know it's practically very difficult to collect more number of data samples like any other field. In such case, obviously like okay, so going for a deep learning with in case of with the newer techniques, it's possible to augment the images. So in a generative model, but unfortunately, in case of a medical images or medical domain, the generative images are not very well accepted. So if the moment like you say like okay, I built a model using the generative images, so then probably like nobody will be even interested in looking into that model. Okay, so why? Because like so they don't trust. Okay, so that is one case. So if that is the case, where you are working on a problem where large amount of data is not available, either it is very difficult to capture or it is impossible to gather the new additional data. In such case, it is always advisable to go for traditional machine learning with the consultation of a proper domain expertise to decide like so what kind of data or what kind of features are the representative of that one. Okay. On the other hand, my data is less, I can still able to generate more number of defect images and I can still use, you can go for a deep learning. Okay. So this is one case. So there are some domain where that is true, madam. Because if you give a X-ray and ask me to like okay, so read it, probably like okay, so based on whatever the interaction I could be able to read it, but I won't be able to interpret like so. Obviously, you need to have a like somebody to correlate, somebody to help you to understand and correlate, like, okay, so to explain that, okay, so whatever your understanding or your interpretation, somebody has to interpret it actually.
How can we say that this concept will be useful in real time for the doctors to explore?
Okay.
Because problem may occur outside also.
So, okay, I understand, like probably you are working or most of you are working. How can you reduce it? So this is the problem not only for the medical engineers, even for us also we will get this one. So we always tell our engineers to communicate smarter rather than like so giving something. So now, doctor's time is very precious, availability is very low. How best you can, what is the best way to utilize the whatever the time frame it is available is what you need to think. See, rather than like, okay, so if you dump everything, all the raw data, if you give it to doctor, probably you may take a lot of time to interpret it and explain it. Rather than you try to generate, like, so I was talking about this pseudo labels, right? Pseudo label is like exactly the same problem what we are facing. So if I give like, okay, so 1 million images and ask someone to label all those images, obviously it takes a lot of time for him. Rather than that, I will try to generate a pseudo label. Not only pseudo label, like, so this is how we try to address this problem. Okay, what we did, initially we were trying to give like all the images to him, and please, like, so these are the images we collected in the last 2 weeks, please label us and give. They used to take like 2 months. Quite natural. Then we try to see like how best we can reduce. So anyway, I have some labels already, training label. Based on that, like, let me generate some pseudo labels. We try to give like, so not only the same set of images, but with a pseudo label. So these are my labels. At least try to verify whether these labels are proper or not. Whenever there is a label is not proper, you try to change, or like you try to reject, to put it into different group. That reduces the time. Okay. So then, what we did, like, so we went one step ahead. How best we can reduce that further? What we did is, we took all the labels, we generated a pseudo label. Before generating a pseudo label, we formed the clusters. From each cluster, I took the sample, generated a pseudo label, and I said, like, so these are the group. This is my variation. These are the pseudo labels. I have let us say like 1 lakh images here. But I given like 100 images to verify. Even it need not to verify 1 lakh images, right? You can just see like 100 labels and you can give like, okay, yes, these are proper or not. So this is how you need to communicate. Like, so basically, when the time frame is very limited, try to utilize your data science approach. How best you can concise and generate a meaningful insight so that you can verify and give the confirmation. So if you give raw data and ask him to verify, and if you want to like extended session with him, definitely it is not possible. Okay. So based on the each interaction, how best you can derive and make a prepare a data in such a way where like so the decision making for him becomes at that point. Clear? So this is for like basically like if you are having very less data and you don't have any mechanism, go for it. Not only that, so you have a less data and less variations. The problem is itself is very, very simple. Don't use ResNet for 50, ResNet 100 for a small problems. So problem is very straightforward. Go with like, okay, so you know like, okay, so my problem is a very limited scope or like, so the limited variation. A simple nearest neighborhood problem or the simple regression can solve. So don't go for a ResNet. Okay, so this is the like these days, this is another advice I want to give. Most of the time, like, okay, so we are trying to overfit the problem actually. So my data is very small, or the variations are very small, but since like so TensorFlow is available, or somebody has already trained like ResNet, I can use it. So without even getting into the analysis, so they try straight away jump into this. So this is based on my personal experience I am telling. So nowadays, most of the time, students talk about like so different APIs, different frameworks. I know PyTorch, I know like TensorFlow, I worked on Cafe, everything is fine. Can you explain like so what is distribution, actually, data distribution. Like how do you define, like, so the dimensionality, if I want to reduce the dimensionality, they don't know anything about that actually. Without even getting into the fundamentals of machine learning, or without even getting into the basic understanding of machine learning, so they blindly jump into using some pre-trained models. See, nothing harm in using any pre-trained. I am not against using any pre-trained model. First, at least do your homework to see, like, whether that whatever the model you selected, whatever the architecture you selected is appropriate for your problem or not. See, sometimes the data set is so small, or the variations is so small, even like, okay, so the Linnet can itself is too much. So blindly they use like ResNet 50. Tell that, like, my data is giving 90% or 95%. I said, like, so is it truly 95%? Are you overfitting the data? They don't know any idea about that actually. So just, so ResNet code is available, ResNet is available, you try to give the data and try to do the inferencing. So that should not be the case. So before using any architecture or any approach, right, try to understand, like, so what is that? What is your data? What is your purpose? Whether that data, like, whether that architecture or the approach is whether really required or not. Those are the kind of things probably you need to always answer before you get into using any model. Right? Okay. So this is just example of supervised learning. So typically I have an image. Purpose is, like, so basically I need to classify whether this image is a indoor image or an outdoor image. That's it. Okay. But basically, what kind of features you can extract? What can decide? Like, so, so the problem is very simple. I give a picture. You are expected to tell that whether that picture is a representative of indoor scene or outdoor scene. Shape. Okay, shape. Objects, shape. How many shapes you will learn? How do you detect the shape? Just think, like, so in an indoor scenario, multiple colors can exist outside also. Okay, lightings. Then, see, most of the time, if you look into the indoor scenario, more or less, if you look into the edges, low-level features, so mostly, like, okay, in the indoor scenario, because it's a man-made objects or man-made structures are available, so the edges are expected to be more structured, like, so more structured in the sense, like, so the linear structures are expected in case of indoor scenario. But when it goes to the outside, so since it's a natural phenomena, the edges need not be very regular. It doesn't mean that, okay, so straight edges are not available outside, but the very less frequent. Okay, so that's the feature being used here. So let us not worry about that anyway. Okay, so in case of a traditional machine learning, we try to do this image. You extract the feature. What is the feature I am trying to extract? The edges. Generally, I try to detect the edges, and then edge similarity, or like, so the structure, like, I will try to study some structure about the edges, and those are used as a feature, and then I try to train the classifier to decide whether it is a indoor scenario or outdoor scenario. Okay. So what is limitation? Like, so limitation is very tedious and costly to develop handcrafted features. Why? So first you need to develop your own edge detector, and then once the edge map is generated, you need to see, like, so edges are regular or not, and based on that you can decide. You need to come up with some index for the regularity index for the edges, and etc. and so forth. So the handcrafted features are usually idly dependent on one application. For example, if you extract a feature for this particular application, you cannot use it the same feature for other application, which is quite similar, like quite natural, right? So for example, if you are extracting a feature for OCR, cannot be used for face detection, or face recognition. Okay, whereas in case of a deep learning, what it will happen? So I have an image. First we extract a low-level features. Then like okay, you extract a mid-level feature. Then high-level feature. Okay. So then you will have a trainable classifier, and then you will get a prediction result. Okay. So these are like low-level feature, mid-level feature is nothing but like we said the number of layers defining your convolution layers. Okay. So this is what the first level of convolution when you try to do, like so probably it will try to extract the edges. Then when you try to perform the aggregation of the features, so it may look something like this. Then like this is the very high level aggregation, and finally like clear, right? So basically like I'm just trying to give like okay, so how does the deep learning works? Deep learning means you are trying to stack different convolution layers to extract the features at different levels. Okay, depending on the you try to perform the pooling operations to aggregate the features and try to learn them, and finally you will have a feature map, and you try to train the classifier, so which is nothing but your fully connected layer, and then perform the classification. Yes, at every stage you basically like if you look into the, I think probably it has been covered. I am just trying to assume that okay. So typically like you will have a convolution layers followed by like some pooling, right? So max pooling or average pooling you are trying to perform. So basically pooling operation is performing two operations. One is of course it is reducing your dimension of the data, okay, or the number of data elements you are processing. In addition to that, it is also performing some kind of aggregation. Basically, when you try to perform a pooling, max pooling within this feature map, basically you are trying to take a representative of this, right? So that kind of aggregation happens. And this happens at the subsequent layer means basically like next layer, you are trying to compute the feature convolution on the aggregated features already. And then when you try to perform the pooling next time, then one more level of aggregation happens. That's all. Like, so we try to construct a feature pyramid in case of the deep learning. When we are trying to learn a features in the convolution, the deep learning layers, basically first you try to extract the low level features, then some kind of aggregation happens. So this is kind of feature aggregation. Probably if somebody worked on traditional image processing technique, probably you know like okay, so this is generally we work on the image pyramid actually, like feature pyramid. So our scale space, so like your shift surf features works on these principles actually. Basically you are trying to aggregate the features at different level. Right? Why deep? Understand it better. So this is what like one of the experiment done by Mr. Frank and Frank et al. So what they did is like okay, so they tried to perform the operation like so where they fix the number of neurons as a 2000. If the 2000 neurons are aggregated in arranged in a single layer, so they were working on the problem of word error rate actually. Basically when they speak, okay, it should recognize the word, okay. If it is not able to recognize, so that is the word error, okay. So that means if I say welcome, it should recognize it as a welcome. If it is recognized properly, it is proper. If it is instead of welcome, if it is recognized something else, that is a error, okay. So what the experiment they did is like okay, so if the 2000 neurons are arranged in only one layer, so they were getting the error rate of 24.2. Okay. So in the next experiment, they repeated the same, data set is same, but they spread across 2000 neurons in two layers. The number of neurons are fixed. Okay, so 2000 they fixed at 2000, but it has been spread across different layers. When the two layers, so they see like so there is a reduction in the word rate, error rate. Okay, so 3 into 2k, etc. and so forth. So that means this experiment shows that like, so even the number of neurons are fixed, when they are spread across different number of layers, so they are seeing like, so there is a reduction in the error rate. Okay. But on contrary, there is a universality theorem. Okay, for this, there is no theorem or like, so the theoretical proof available actually. Okay, this has been empirically proved that, okay, so there is a as the number of layer increases, so there is a performance increase. But the universality theorem says that for any continuous function f of this form, like function f which maps Rn to Rm, so which is typically our machine learning problem, right? So what is machine learning? How do you define machine learning? So I have n number of features, or like I have extracted a feature which is of dimension n, and I need to classify this n number of features into m number of classes. That's right. I need to find a function f which can map a instance of this to this, which is a machine learning problem. Now, what this universality theorem says that, okay, so you take any continuous function f, this can be realized by a network with only one hidden layer. So, which is contrary to your deeper layer. So, there is a proof available for this. That means like, so there is a mathematical proof available which says that, okay, you can take any function f which can be realized by a network with only one hidden layer, provided I should be having enough number of neurons. Only one layer, but you should be able to stack enough number of neurons in one layer. If that is the case, you take any function. If this is the problem, you can solve it. All of you are able to follow me? So in the previous case, we were talking about the deeper network. So deeper network means, so not one layer. So increase the number of layers. We were able to see reduction in error. But I cannot state any, we cannot prove that. So though the performance is empirically shown, so we cannot prove it. But the universality theorem, there is a proof available, and it says it is true for any function of this form. Now, why, in spite of this theorem, why like, okay, so the deep learning or the deeper networks are more popular, then probably I will call this kind of network as a fat network. Why fat network? Because we are trying to have fat number of neurons, only one layer. Getting the point? Problem is, we never know how many numbers I need, number of neurons I need to stack. One, and so training this kind of network may become extremely cumbersome. So that's the reason the fat networks are not so popular compared to the deeper network. Okay. So another interesting factor why deep learning becomes more popular, though like it lacks the sound mathematical basis, is because of its modularity. Modularity in the sense, see, nowadays like, okay, so probably if somebody asks you to implement a CNN from a scratch every time, probably CNN would have not become like a deep learning would have not become so popular. Now like, okay, so what is, so you just implement a convolution layer, and like any number of convolution you can stack it. So implementation of platform or a package itself is very, very simple, and there are many packages available which support this kind of implementation. So you are like, you are just trying to add. Probably, I think probably if you are familiar in using TensorFlow or PyTorch, you know, like, okay, so you can just create a structure and you can just add. So add layer, convolution, CNN, so many number of filters. So what kind of convolution you need to perform? So think about like if you want to implement that by yourself, probably you would have not, or deep learning would have not become so popular. Okay. So because of its modularity, it's easy to implement, and because of that, like, so it becomes more popular. Okay. So this is what the fat network I mentioned, like, so, right. so more number of neurons. So it's these kind of networks are called shallow networks. Whereas in case of a deep network, so you will have like so multiple layers. So the number of parameters are almost same, but output performance could be really different. So why? Because there is a refinement happening at every layer. So that doesn't mean that, okay, so this is incapable. This network is not able to solve that problem. Yes, it can solve the problem. Probably it may require more number of neurons. That's what universality theorem says. You can solve this problem, but probably you may need to have more number of such neurons. How many? Clear? So, yes. How many? Where in case of a deep neural network, right? Yes, both are same. Like even for a deep neural network, there is.
I have already faced some type of question in some interviews. Up to what level we can say that is machine learning, and up to what level we can say that is deep learning. Up to how many hidden layers should be there?
See, typically
so
like okay, so for that, like so nowadays, like in your deep learning, right? So especially if you are using a CNN, you can see like okay, feature visualization actually. So at every level, like so we have something called CAM, class activation maps, right? So just by looking at the class activation map, you can see that okay, so whether adding any additional layer is required or not. So whether you are just before your FC layer, so it is more or less it is capturing the essence or like so the input patterns, right? So then it is sufficient actually. You need not to add any additional layers. Okay, so I think probably all of you are familiar, right? So this question is. So in case of our deep neural network, how many layers I need to keep adding it actually? So one way of doing this is, so at every level, after every convolution layer, you can see that the CAMs actually, class activation map. So which visualizes how much each layer has learned about that class actually, about that data, input data. So at some level, it is more or less representing your input data, right? So that means that, okay, so this number of layers are sufficient. Then you can go ahead with the FC.
Sir, but it depends upon the number of project and number of features we have, right? But we cannot say that universally on this number of layers means machine learning.
No, so there is nothing like universality. You cannot tell that, okay, so I have a medical imaging problem of classifying it as a tumor or not, and I will use only 3 layers or 4 layers. That is not decided. That is not defined.
Because in some interviews I have faced the question, that's why I asked.
Okay, so that is not the case. Like basically, you need to look into the complexity of the data also. Okay, and what you are trying to achieve. So based on that, like so only you can decide that.
Thank you, sir.
Clear? Okay, so this is about the number of parameters. Like okay, so this is one more case where they are trying to see like different number of parameters. Okay, layers into size. So only one layer with this many number of neurons, one layer with this, and one layer with this. So they are the performance like so it's more or less like same. Okay, whereas like so with the number of the parameters is fixed, and this is the word rate decreased. Right. So it clearly shows that so the deeper network is able to represent the data in much effective manner. In this case. Here like so the same thing is not been shown like so with the fat network. Probably it requires more number of neurons, so which probably like so take a lot of time. Okay. Which one? Right, it's a number of layers is fixed, one layer, only one layer, they are just increasing the number of neurons. So from 3,772 neurons to 16,000 neurons in the same layer, so the word rate decrease is not significant. Whereas in the second case, the number of neurons is fixed as the number of layers are increasing, so the performance you can see that.
how many number of layers, the neurons in each layer again. Again, as we discussed, what is the number of neurons in fatty network and how many number of layers in deep learning network. How many number of layers in each, neurons in each layer again.
So in
Based on
case
the
of a
feature.
deep network, like how many number of neurons has to be put
in
in?
each layer. That also may vary now. In one
See,
hidden
that
layer-
one, like okay, anyway, we have a empirical method to say like how many number of neurons, like maximum number of neurons, you can based on the input output parameters, you can decide that. Right? So that is. Okay, so to decide the number of neurons in each layer, so there is a empirical formula available, like so which is a function of the number of the output layers and the number of inputs possible, right? So based on that, you can always define the maximum number of neurons in each layer.
Sir, but the number of neurons in input layer and output layer we can fix based on the requirement. As in input layer number of pixels or somewhat, output layer number of resultant. But the hidden layer may vary.
Hidden layer also same thing, right? Like basically it's a modularity. So now for the next, so if you are talking about the second layer, so which decides the number of inputs for that second layer? The number of outputs of the first layer will be defined. So that way you can define the number of neurons for each layer actually. Okay. So yeah, yes. Huh?
Universality theorem.
Uh-huh.
Within one layer, we have lot of hidden neurons. You can
Solve, yeah. So,
so whether that there is controversy to this slide here. Remember 1 into 16K. That word error rate will be 22.1.
So that means here also there is a see there is a decrease in the error. Even in this case, there is a decrease in the error rate, but decrease is not happening that drastically. Here, just by having 7 layers, so there is a drastic decrease in the error rate, right? But here also a decrease is happening, but even with the 16,000 neurons, it is not that drastic. Probably, see, what universality theorem says, but provided any number of, like many number of such neurons should be available. Probably like, if not 16, probably if you add 1 million, you may get similar kind of performance.
So ultimately, one hidden layer with many number of
Neurons? Yeah, that's what the universality theorem says. Any continuous function f. So if the Rm to Rm mapping is possible with only one hidden layer, provided many number of neurons is added. Any number of, how many number of neurons? That is not defined actually. You need to keep on adding that neurons actually. That is the universality theorem. So here it is showing that, but so even with the 16,000, the error rate is not drastic. That's what I just wanted to show, like it's just for the comparison. Okay.
One more thing I want to say, sir. As you said, if people have done that export that the CNN, then deep learning won't become such a big thing. So whether can we say like this, DNN is equal to CNN, like that, shall we project like that?
CNN?
You said, no, if people have worked the CNN properly, with more number of CNNs, then deep learning won't become a big thing. So whether we can say like now, as I said, the universality theorem is compromising this. So can we say the same thing that people have worked a lot of CNN deep learning won't be a big thing like that? Is it possible to can prove and can we do it as a paper and whether it will be proper?
Definitely it will be a good paper actually. Even if you prove that, okay, so DNN is failed or like, so it is same performance, any theoretical proof, right? It's definitely it's a good paper. But unfortunately, like, so at least to best of my knowledge, no such theoretical proofs are available with respect to the DNN actually. But there are many empirical studies in the similar line has been made to show that like, so with less number of parameters or very optimal number of parameters, like the performance is really good. Those kind of study has been done, but not a theoretical proof. Any such theoretical proofs, at least to best of my knowledge, I didn't encounter any of such thing. And any attempt in that direction could be really a good contribution. Okay. Any questions? Quickly. Yeah, I think okay. Well, this we already talked, right? So why deep learning? Like so, one is the more number of layers, and more so because of the modularization. Modularization means so you can repeat same thing. Like okay, so every layer. So though you are trying to perform certain like so every layer is trying to perform trying to get different features. Okay, so basically like underlying implementation remains same actually. Like so you are trying to having same kind of convolution or like so same kind of operations being repeated every time. Okay, so that's what like so the modularization. So if you have like okay, so it's as good as like okay, so with a one layer means you are trying to learn all classification at only one layer. Okay, whereas in case of a deep learning, you are trying to first classify whether it is a boy or girl and or like it's a long hair or short hair, and then subsequently you are trying to train like. So that means, so the deep learning, every layer like your input is getting refined. So that you can easily clearly see that. Okay, so that way your problem is transformed into smaller problems actually, like at every layer. So it is getting transformed into a much towards your final objective. Okay, whereas in case of a fat layer, it will try to solve the problem at a one. I think probably if you are from a computer science, probably you know already know, right? So divide and conquer is the simplest way of solving the problem. Like so, basically you try to divide. Basically in divide and conquer, you try to divide the data. Basically like it's something like okay, dynamic programming. Basically you're trying to solve the problem into sub problems and try to combine it actually. So in the similar way, basically your deep learning, because of the modularity, it will try to transform the problem at every layer. Okay, so I think probably if you already seen that class activation maps at every layer, you would already realize that okay, how the data get transformed at every convolution layers. If you have not done that, probably please try to see how your class activation maps at every layer. You can see like literally visualize the data getting refined at every convolution layer. Okay. Yeah. So this is how your the deep learning, like if I try to put it. So you will have a most basic classifier, and then like so output of this will be consumed by the next layer. It will try to build next level of classification, etc. and so forth. See, when I say deep learning, don't only visualize CNN. CNN is only one instance of deep learning. Okay, so the deep learning can be applied for even your non-image data also. Okay, or your any other form of data. Okay. So deep learning basically you'll have many feature learning layers followed by fully connected layer. Okay, so in case of CNN, your each layer will be a CNN layer. Okay, but in case of other networks, other form of modality of data, it could be like still performing a similar kind of operation without performing any CNN operation. That's it. Okay. Now nowadays we are talking about a different type of operations inside that each layer, right? So one is of course convolutions. So we are talking about the morphological neural networks, MNNs. So for example, I don't want to learn about the basic primitives like edge or the pixel or the corners. I want to study about the shape and structure. So we talk about MNNs, morphological neural networks. Right? Each layer, so instead of CNN, convolution operation, you will have a morphological operation like eroding and dilations operation. So then it will become NN. So similarly, like okay, so we have a different type of operations you can always embed, but the underlying concept is same. And somebody like okay, so if you are working on a medical images and you want to study like low-level features like edges and other things, and you also want to study about the shape and structure, then you can combine like okay, so CNN followed by your MNN kind of structures to come up with a very, very interesting results. Okay. Don't get confused that okay, so deep learning is only CNN. CNN is only one instance.
Same way for face recognition also. Face recognition, in that case, if we want to transform the 2D data to 3D data, in that case, how this mapping should be done.
Yes, quite possible. So we are talking about like, so you can perform the 2D convolutions. If you want to perform like so 3D convolutions, you still perform the 3D convolutions. And sometimes like so, if you don't want to perform on the spatial convolutions, like so voxel convolution, that is also possible. So typically we try to, most of the time you will have like 3D rendered data, and you want to perform certain kind of operations on the 3D data, you can still perform that. Okay. See.
The depth sensor is a kind of sensor. From that we are getting the data. So with that we can find out whether patient is in anxiety state or whether due to anxiety or due to stress the space is bulged or not. So for that case we can use the same of
See, you can use any kind of operation. So that see, if you feel like, okay, so those kind of things you want to study with only convolution, you can still do that. But if you feel like, okay, so you want to study only the structure and shape of the objects, you can still use the RNN or combination of, not morphological MNN, and combination of these two is also possible. Okay. Yeah, CNN and MNN. See, there are a lot of research is happening in this area. Like, okay, so now we are talking about the graph neural networks, GNNs. Okay, I don't want to train it as a like a CNN or the MNN. I want to train it as a graphs actually. Okay, so we generally like so that's what like your GNN looks comes into graph neural networks. You can construct any kind of scenario like, okay, so instead of a regular structure like this, it could be any graph. And you can form a graphs, and then like, so each node in a graph could be one CNN or MNN. So that way you can try to see. Typically what I meant by GNN is, see now for example, so this is my graph actually, like so some kind of operation has to happen. So here I am trying to study like what is that, like the basic features. So probably I will use in this node I use CNN network. Here I am trying to study the shape and structure from the same input. So then probably here I am using MNN. So here like, so from this same data, I am trying to extract the text. So probably here I am using so just DNN, deep neural network. And trying to combine all this information and try can perform this operation. This is one way of solving the problem. So generally like graph neural networks try to handle this kind of thing. And we also talk about the staging classifiers. Staging classifier means, so I try to perform the classification, different classification at different stages. First, I will try to do the anomaly detection and then followed by classification. Or like, so I try to combine different inputs at different layers. Those kind of things are all possible. That is the variants you can always think about. Okay. Clear? Okay, so this is the rationale between like, okay, so typically if you have an input space, so these are the input data, like so what traditional machine learning will try to find. So you will have like a decision boundary. So typically SVM will try to transform your data into a higher dimension space where so that I can find a linear separating plane. So this, whereas in case of deep learning, you have an input. So at every layer we try to transform the features, like so from the learnable kernels, you try to learn the basic features, and then, so this is what like so your feature extractor or the feature learning modules, and once the features are learned, you will have like, okay, so the final classifier, which is nothing but FCNN, the fully connected neural network, and then you will have a final classifier. I am just assuming that, okay, you are already familiar with how does the neural network works, okay. So basically when I say FNN here, fully connected FCN, so it is nothing but your traditional neural network. How does the traditional neural network? So till this, you are trying to learn the feature. So if it is a image, if x1, x2, xn are the images, so you perform the convolution operation, and once the convolution operations are done, like, okay, so whatever the data available, after this last layer, you just try to perform the flattening operation and then give it to fully connected layer. And if it is not the image, these are the textual data, like so some numerical data, just perform like same kind of numeral operation like traditional perceptron models, and you will have like whatever the feature you extracted here, so you will just give it to your neural network and it will try to perform the classification. It's hard to say, like, so depending on so how much data or how complexity scenarios you are handling. So based on that actually, because if you are handling like so very small population of data set, probably like okay, so your iterative model can still work. But when it comes to larger variations and like different pose and different lighting conditions, probably your iterative model may not be able to handle all the scenarios effectively. In such case, probably deep learning can effectively handle those cases. And also like, okay, so training these kind of systems may be like much more straightforward and easy to handle compared to your iterative model. Okay, so let us see like, okay, so how does it work? Just we'll try to see a basic neural network for this. So basically I'm just trying to answer how the CNN came into picture actually, okay. So let us say like we have 4 inputs, x1, x2, x3, x4, and I have one hidden layer with 4 neurons, okay. This is another activation function and one output layer. Clear? My problem is I have 4 inputs, one hidden layer and one output layer. If it is fully connected, how many parameters are there in this network? How many parameters you can learn? 4 into 4 here. So this is activation function anyway. Sorry. And here 1 cross 1 actually. So basically how many? 16 learning parameters. 4 into 4. Here 1 learning parameter. So basically bias or your and then 1. So this, I think probably this you are all familiar, right? How does it work? Okay. So typically for A1, so if these are the weights. So basically like, okay, so what kind of operation happens here is, if it is a perceptron model, it's nothing but a weighted summation of all these inputs, okay, and then like, so it will be applied on some activation function and that will be the output. So this is the kind of operation performed in this node, W1 into X1 like this, and then some activation function F is applied. So activation function could be any type of activation function. So now if you take this totally, so this is your softmax function. So these are the number of operations you can learn, like so 4 into 4, 4 plus 1 and 1 operation. So the number of parameters, learnable parameters for this particular network is this, okay. Now let us see the image. I have this image 400 cross 400 into 3 channels, okay, RGB image. Now if I want to apply this neural network for this image, problem is same, classifying whether it is a indoor or outdoor. So let us assume that I will have like, okay, only one, this is my input layer. So if I try to stack all the pixels into one layer, okay, as it is, so then I have like so many number of inputs. It's a 4,80,000 pixels, right? And if I use only one hidden layer, with same number as the size of number of neurons in this layer is equal to the same number of neurons as that of the inputs, and one out. So then the number of learnable parameters for this problem is 230. Clear? Okay. So very simple. So what I did, I am not even worried about like convolution or any operation. I am just trying to take this image and converting each and every image pixel value as a numerical value, and I try to arrange them in one order. So now the number of inputs turns out to be 4,80,000 inputs, and I am having only one hidden layer. So even if you consider very simple network like this, so the number of trainable parameters is 230 billion. Can you imagine, like, okay, so what happens if the image size is more? It increases. If it is less, right? Okay, so now even if you take, like, okay, so I don't want to keep the number of neurons in this layer as same that of the inputs. Even if I try to keep only 1000 neurons in the layer, I'm not even talking about whether it is a meaningful architecture or not. I'm just trying to show, like, the complexity, right? So even if I take about 1000 neurons in this hidden layer, so still, like, okay, so the number of parameters, the trainable parameters is 480 millions. Clear? So this should be able to convince you that why CNN? Okay, we are not talking about the deep learning. So at least for, like, okay, so why CNN has been thought of actually, like. Okay, so yeah. Tea break? Okay, I'm okay. Okay, we'll take break. How about you guys? Like, so, huh? It's okay, sir, no problem. Okay, yeah, sure. Okay, we'll take a break for a while.
ದಿನಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋತಿ ಬದುಕು
ದಿನಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋತಿ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋತಿ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋತಿ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋತಿ
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಜ್ಞಾನದೇ ಗುಲವಿ ಬೀಡು ಬಿಟ್ಟಿದೆ ಕಡಲಿನ ತಡಿಯಲ್ಲಿ ಅರಿವು ಮೂಡಿಸುವ ಗುರುವೆ ದೇವರು ನಮ್ಮ ಈ ಗುಡಿಯಲ್ಲಿ ಎಲ್ಲ ಸಾಧನೆಯ ಮುಟ್ಟು ಮೆಟ್ಟಿಲು ಹತ್ತೋದಿಲ್ಲೇ ಮೊದಲು ವಿದ್ಯೆಯೇ ನಮ್ಮಯ ಹಕ್ಕು ನಾಳೆಯ ದಿಕ್ಕು ಜೀವನದ ಸೆಲೆಯು ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಬೆಳಕು ಜ್ಞಾನವೇ ಬೆಳಕು
ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋತಿ ಬದುಕು
ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋತಿ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋತಿ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋತಿ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋತಿ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋತಿ ಬದುಕು
ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಜ್ಞಾನದೇ ಗುಲವಿ ಬೀಡು ಬಿಟ್ಟಿದೆ ಕಡಲಿನ ತಡಿಯಲ್ಲಿ ಅರಿವು ಮೂಡಿಸುವ ಗುರುವೆ ದೇವರು ನಮ್ಮ ಈ ಗುಡಿಯಲ್ಲಿ ಎಲ್ಲ ಸಾಧನೆಯ ಮುಟ್ಟು ಮೆಟ್ಟಿಲು ಹತ್ತೋದಿಲ್ಲೆ ಮೊದಲು ವಿದ್ಯೆಯೇ ನಮ್ಮಯ ಹಕ್ಕು ನಾಳೆಯ ದಿಕ್ಕು ಜೀವನದ ಸೆಲೆಯು
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು
ಜ್ಞಾನ ತೆರೆ ಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋತಿ ಬದುಕು
Okay, so one can generate that kind of labels. The problem is like probably you will have large amount of unsupervised data. That means without no labels. So now I need to generate this labels for this data. Okay. So that again calls for like this annotation. Somebody has to sit and do the annotation. So yes, those kind of tools will help you to accelerate the annotation process. But my question is there is any way we can automatically generate a label? Because any supervised learning, right? So you need to have like, okay, so data and corresponding label to train. So now I don't have this. Is there any way I can generate the label? That was the okay. Mm-hmm. See how it will, so whatever the tool website you said, right, how it will come to know that, okay, so what kind of label has to be assigned. See, I will give like, okay, so for example, let us say this is my, our data set like this MLCC chip, this is electrode, and there is a body defect. I want to classify this as a body defect. So similarly, like, okay, if there is any defect in the electrode, so I should have electrode defect. How to generate these kind of labels? You have to sit and do the annotation. Is there any way, like, okay, so one is, that is the straightforward, like that is what is expected. So if it is, huge amount of data, like, so I have a millions of such samples. How do you generate that kind of label is what. So as madam said, one way is do the cluster. At least since your problem is a classification problem, at least you are trying to generate a label for a classification problem, you know like how many classes your data has to be classified into. Say for example, if my data is whatever the samples I collected, it should be classified into 20 different groups. Okay, I will create a clusters. I will try to perform the clustering with expecting 20 clusters. So then probably like, okay, so you will get 20 clusters, and then you can use like, so 20 clusters, you cannot directly use those clusters as a labels. Clear? So basically it will group the data into 20 different clusters. So somebody has to still look into this cluster and try to see like, okay, so whether this cluster is corresponding to defect type 1, defect type 2, defect type. Once this is done, then probably like all samples inside this cluster will have a same label D1, D2, etc. and D3. Clear? This is one. Do you see any challenge with this approach? That is okay, straightforward. Like, so instead of checking 1 million images, probably hardly you need to check maybe 20 or some 10 samples from each cluster, and then you can still do that. The grouping, how do you, okay, first problem is, how do you ensure your clustering itself is proper? Okay, of course, like, so there are many ways to evaluate the goodness of cluster. Like, so we have a cluster indexative, cluster evaluation methods with which you can decide like, so whether the clusters are properly formed or not. Okay. So what is the intercluster and intra-cluster dependency, like, so what is the variations, those kind of things. But still like this kind of approach, clustering approach works well if the separation is clear. See for example, like separation like this, hardly our images are like, so maybe 100 cross 80 or 100 cross and defect size maybe like few pixels. So in this case, probably like what kind of features you are going to use to do the clustering, that itself is very cumbersome. See, I cannot directly cluster the images, right? So somehow you need to represent these images in terms of its representative features and then perform the clustering. How are you going to, how do you decide what type of features? See, even in case of your medical images, if somebody is having a medical images and you want to group it, on what basis you will group it? Okay, clustering, okay, I will use k-means clustering or some clustering, I know like, so the number of clusters are expected, those are all fine, but what data, what features you are going to extract, that is very critical. Okay, so for that also, see, that is the beauty of deep learning. So what you can do is, you need not to extract the features, okay, you can have like, okay, so CNN or like, so some network built, so you pass the image, so after your FCN, fully connected layer, discard this, you take this feature representative and then perform the clustering. That is still possible. You can always separate it out and you can do it. But always ensure that whatever the features you have learned here is capable or good enough to capture these smaller variations. Okay. So in fact, like, so in one of our problem, we try to utilize this kind of approach. So especially for, we manufacture PCB. For phones and television, like, okay, so in PCB there could be some kind of very peculiar defects. So especially like the foreign bodies. That means like typically when we manufacture these PCBs, so there is a clean room process. So in that clean room, there should not the number of suspended particles should be less than 10 millions per 10 ppm, like we say, like, so 10 million. Less than 10 particles per million. So that is the kind of environment. So what happens if there is such kind of foreign matter? So then like, okay, so the when we try to fuse one layer of PCB on the another layer, So the electron conductivity will not be very, very appropriate. So we need to identify that. So, but when we try to use the clustering technique, so we are assuming that, okay, so 4 type of defects, and we could able to see that, okay, so the algorithm was not able to capture that all the 4 defect classes effectively. So how we try to do is like, okay, so we increase the number of clusters. So though I know like, okay, so there is only 4 clusters expected for this data, we made the number of clusters as 8. So I am purposefully allowing it to form 2 different clusters, and upon verification, we try to merge these 2 clusters. Okay, so that way we try to handle it. But there are multiple approaches you can try to do. Clustering could be one approach to generate the labels. Okay, any other thoughts to generate the labels? Okay, so other approach could be like this. So you have some labels. Okay, so it's just like semi-supervised level. Use these labels, use this labeled data to train a classifier. So now I have a classifier. This classifier built on the some small set of data. Now you give all your unsampled, unlabeled data to this classifier. It will try to classify, right? So basically this is a classifier having the same number of, same behavior of your expected classifier. So based on this, you try to generate a labels or the output inference. So one is using that labels, you try to call it as a pseudo labels because it is not yet verified. You can call it as a pseudo labels, and you can use those labels to verify or get it confirmed that, okay, whether this. Now, what is the problem with this? Problem is, whoever verifies, he end up verifying all the samples. Though he is not manually labeling the samples, he end up in like labeling all these samples, right? So to overcome this problem, what you can do is, so you have a classifier. I don't only save the output of this classifier. In addition to that, I also store the confidence ratio. So whenever you try to do the classification, you also get the class confidence ratio, right? So from your final softmax layer, you try to capture those things also. And if the classifier is very confident about a particular class, you can just ignore that. No need to verify that because I'm absolutely sure that, okay, so this is properly classified. And whenever there is a confidence ratio is in certain range, like, okay, so 40 to 70, only those samples you try to get it verified, cross-check it. This is one way. And if at all you want to make much more robust, so you have a labeled data, right? Small set of labeled data. You split this into 2 or 3 folds. Okay, using this, I build a classifier 1. Using the complementary of this, I build a classifier 2, classifier 3, or whatever it is, like a number of classifiers. Now, data is given to both the classifiers and try to see what is the confidence and the label. If both the classifier says it's the same label with a high degree of confidence, I am absolutely sure that, okay, the label is proper. Whenever there is a conflict or the confidence score is low, then only you try to send it for. So these are the different way of generating the pseudo labels or auto labeling actually. Okay, so this comes under the category of semi-supervised learning. So this can be utilized while building like automatically labeling your data sets. Clear? All right, so let us continue with our discussion. So we'll try to see like, okay, so how the convolution can reduce or help in handling this problem. Okay, so this parameters really varies with respect to the image. If the image size increases or decreases, this can vary. If you increase the number of layers or the number of neurons, still it can vary, right? So now, how do I contain it? Is what like so we are trying to. So this is what like generally we try to do in the convolution. I think all of you know what is convolution operation, right? Convolution means, so I have an image you will have some filter. Okay. So you try to, how do you define convolution? What exactly convolution operation is? Hmm. Yes. For what? Hmm. So basically, like, okay, it's a filter, right? Basically, you are trying to see, like, okay, so what data, type of data you want to highlight, or what type of data you want to suppress. Okay, just like, okay, so any traditional filter, what we try to use it in our day-to-day life. In the similar way, so in the convolution operation, so depending on, like, so what kind of filter bank or the filter I try to use, I am trying to either highlight or I am trying to suppress certain kind of data. That's it, and a very layman's term. Now, how do I perform the convolution operation? So typically convolution was defined in a frequency domain. Okay, nowadays, like, so we don't even want to strain our brain with the sound mathematical way. Like, so we forgot the Fourier theorem and Fourier transformation. So now we are talking about, like, so in the spatial domain. In the spatial domain, the operation is very simple. So I will have, like, a sampled representation of this filter. So this could be like, okay, so this is a filter and this is its spatial representation. Okay. Now I take this sub matrix, or like, so this matrix, small matrix. So image is my bigger matrix. I place this small matrix on each and every location, each and every value in the every cell in this bigger matrix, and I try to perform certain operation. What is the sum operation? It's a sum of products. Right? So basically first I try to perform the product. I multiply this value with the corresponding pixel value plus this value and this pixel value, etc. and so forth. And that will generate a response of this filter at this location. And I will try to copy that in the output location. And whatever I get as a output is a response, filter response of this image for this filter. Okay, so we generally call it as a response image. Clear? So in other words, so convolution operation is taking this small matrix, placing at each and every element in the bigger matrix or the image, and performing sum of product operations. Okay, every time I will try to just multiply the pixel value and the corresponding weights. Okay, and I try to generate a response, and that response will be copied into the output image. Clear? Okay, so this is how it looks like. Okay, so your image looks like once it is sampled, it's a matrix. I have this small matrix. I try to perform this operation. That's it. That's all the convolution operation. And if you are familiar with image processing, so you can see, like, so what type of filter it is? It's a edge detector. Huh? What filter it is? See, that is the problem. All of you are very good in image processing. Because of CNN and deep learning, you forgot the basics of image processing. And now you need not to worry about it, right? Now no longer, like, nobody worries about what is image processing. What is this filter? Edge detector? How many of you say, like, it's a edge detector? Because you are seeing edge, you are telling it is a edge detector. Okay, so let me, whether it's a high pass filter or a low pass filter. Sobel? How does the Sobel has this one, right? Sobel require, like, any edge detector will have, like, so two filters, one in x direction and y direction. So because you are computing the gradient. Here I am not computing the gradient. See. After some time, like, okay, so people will ask what is image processing. Okay, so this is a high pass filter. Basically, I am trying to pass the high frequency and suppress all the low frequency component. So why do you say, like, it's a high pass filter? So you try to sum it actually. Like, okay, so basically, you are trying, like, okay, so wherever there is a uniformity in the image. So assume that, okay, so this is if I try to multiply this filter on a pure white background, what will be the response? That means the background is having same value. If I try to multiply this, what will be the output response? Hmm. So that means it is suppressing what? The low frequencies. Whenever there is a uniformity, we say it is a low frequency. It's a low in frequency, lower frequencies, or no frequency. And it, when do you get the response is high? The response is high is only when there is a transition. So transition is the place where there is a higher frequencies, right? So this filter is a high pass filter. That means it passes high frequencies to a low and attenuates all low frequencies. Okay. So this, when I try to perform the convolution operation on this image with this filter, this is what the output I get it, right? Okay, so this is fine. So convolution operation, I think probably I already explained, right? So this, if this is the image, and these are the weights. So if I try to place this at every location, assuming that, okay, one of these is a pivot point, A into W1, B into W2, E into W3, and F into W4. And you sum all these things, apply that averaging or whatever the operation, you will get the response H1. So now move to the next location, repeat the process. You will get. Now look at this operation actually. So what is the image size? 4 cross 4. What is my filter size? 2 by 2. So how many parameters are there? How many parameters, learning parameters in this case? Because it's a convolution neural network, if I want to learn the weight, which weights I need to learn? I need to learn the weights of this convolution, right? So that's what it try to, like, even in case of your network, like neural network. So what is that learning parameter? Learning parameter means what? What you are trying to learn? You are trying to learn the weights between the edges. So in the same case here also I am trying to learn the weight. Here I am trying to learn the weights of this filter. Okay. So now number of parameters for one feature map is 4. All of you are able to get me, right? So in case of the image data, if my image is 100 by 100, how many pixels are there? 10,000. So 10,000 input values. So if I keep 1,000 neurons in the hidden layer, 10,000 into 1,000. So many number of weights you need to learn, and then subsequently how many, whatever the output layer. Now here, this is my input image 4 by 4. So this is my one filter bank or the filter map, feature map. So all I need to learn is 4 values. Now you may say, okay, so in previously you gave 400 by 400. Now you give only 4 by 4. That's why it is only 4. Now let us say, like, okay, so I will increase this image size to 400 by 400. How many features, how many parameters you need to learn? What are the learning parameters? More? More or less? More? More? How many say more? How many say same? Same? Why same? Because irrespective of the size, whatever the size, you are going to learn this only 4 parameters, right? If I increase this filter size, then it will increase. Otherwise, the number of parameter you are going to learn is still 4. It is not going to change, irrespective of the. On the other hand, in the previous case, if my image size is 10 by 10, 100 features, 100 parameters. If my image size is 100 by 100, 10,000. Here, irrespective of the image size, the number of parameter you are going to learn is still the same. Okay, so that way the size of image doesn't matter. The number of learning parameter depends on the size of the filter and number of filters. Clear? Look at the case. Even if it is a previous case, even if you consider like so 400 by 400, So if you use one filter like this, you will be learning only 4 parameters. Even if I use 100 such filters in one convolution layer, so still the number of learning parameters is 4 into 100, only 400, not in terms of billions or millions. Getting? Look at the beauty, like, okay, so how they come up with, like, okay, so the CNN approach. So this is how, like, the CNN originated. Like, see, every invention, like, so everything, see, that's what, like, as a researchers, my suggestion is always see, like, okay, so what is your problem you're trying to solve? What exactly, like, see, always, you should always have the goal and what is your current state. From this current state, how I still achieve my final goal. So if you deep dive into that one, then you can come up with this kind of approach. Otherwise, if you blindly follow something, so you will still generate some result, and result is just left open for your guide to interpret. You don't even take the burden to interpret your results. I'm sorry to say this, but this is what at least I experienced with my students actually. Most of the time, I ask them, like, okay, so what is your opinion? When they generate the result, what is your opinion? Like, so can you interpret and come up with your conclusions? So most of the time you left that open for your guide or somebody else to interpret or conclude. Okay, so don't do that actually. Like, okay, so as a researcher, please, your objective is to understand, like, so what you have generated. Okay, what you have generated is meaningful or not. You made some assumptions. Is it meaningful assumptions or not? Okay, unless you do that, I think probably, like, you may still doing something, but you may not be able to converge. You are not really converging into your final goal. Getting me? Clear? So a very simple concept. So they started with the problem. Oh, I have an image, like, so image size, like, so my parameters are varying with respect to the images. How best I can contain it? How best I can bring it into under manageable case? So they come up with very, very simple, interesting term, and hence, yeah, like, so something called convolution neural network. And because of that, unfortunately, you are started forgetting the fundamentals of image processing. Clear? Any questions? Okay. So now, what are the parameters you need to, like, okay, if at all you want, if you are working on a CNN network, I think this is clear, right? Like, so why CNN, how CNN plays a vital role in reducing the number of parameters, the training parameters. Now, if at all you want to control, if at all you want to improve the, like, so if your result of such CNNs depends on the depth. What is the depth with respect to CNN? I think most of you are familiar in using DNNs, right? What do you mean by the depth? Number of layers or number of number of filters or number okay, I should not use as a filters, feature maps. Number of feature maps or number of layers or both? Layers. Okay, so it is, one is, if you are using the number of layers, of course, the number of layers, and within layer, how many filter banks or the feature maps you are trying to use, both. Okay. So your hyperparameter depends on this. Stride. What do you mean by stride? Okay, whether you want to have a overlapping or shifting, non-overlapping. Okay. And of course, like, so whether you want to have a zero padding or, like, so non-zero padding. So depending on that, your output feature map depends. So this, I think you are familiar, right? What is zero padding means? So whenever you are trying to use the filters, so on the border there is a problem, on the edges of the images. So performing a convolution operation is having some problem. So to address this, so sometimes they try to omit the edges, or sometimes if the results are very, very crucial even at the edges, so then you can use the zero padding or replicating the corresponding rows. Okay, so then, like, okay, we have something called pooling. So pooling is basically to So most of the time if I ask pooling, so the common answer I get is like, so pooling is to reduce the size. Okay, of course it reduces the size, but at the same time it is basically aggregator. So it will try to do like, so when you are trying to construct the feature pyramid, right, like, so pooling helps you in generating that, constructing that data aggregation. So again, pooling, most widely used pooling is max pooling. Max pooling means trying to take a maximum among that feature map, like, so whichever, like, so you will have 4 values, among that 4 values, so whichever is the maximum representative, you try to take that as a maximum. Or sometimes you can take the average pooling, and even you can take minimum pooling also. So it all depends on, like, say, your objective and what you are trying to highlight. So most widely used is the max pooling. Okay, so this is a just example of the pooling operation. If this is the feature map or the response of a feature map, so you want to perform a pooling, max pooling here is, so among these 4 values, whichever is the maximum response, right, you got from the response, whatever you obtained from the convolution operation, you try to take that as a representative. So in this, basically I am trying to take 4 as a representative. What it means is, so within this feature map, okay, so this is the response from a convolution operation, right? Now within this area, what is more highlighting is what we are trying to search. So max pooling operation will try to say, okay, so in this 2 by 2 area, so there is one pixel with pixel value 1, 3, 2 and 4. Getting me? So now, probably, see, everything will create a value. Everything has a value. But when I am trying to look from a next level, probably like, so this is the one which will be more appealing. So that's the thing, I am trying to take this as a representative. Okay, so that's how, like, the aggregation happens. So same thing here. Here. Clear? Stride, I think probably all of you are familiar, right? Like here stride we have kept it as a 2. That means without any overlapping. So that means, so if I try to take the maximum pooling here, so this is 4. So now when I try to move the next, I am not considering any overlapping. So I set stride as 2, so that's why I am trying to take this. Okay. Okay, so this I think probably just to show like how can you construct. So for a very toy problem, I think probably you are already familiar. So problem example here is, I want to classify whether the image is X or O. Okay. So this is basically like you have a very some samples of X and some samples of O. So basically like this is the feature map what I have considered, and try to perform the convolution operation. Clear? So if I try to perform the convolution operation here with the same filter map, so this is the response. How did I get 0.55? Basically you try to multiply 1 into 1 minus 1 into 1. So again it is 2 minus 1, 1 plus 1, 2, 3, 4, 3, 4, 5. So 5 by 9. So basically we are considering like, so 9 values, right? So you are just trying to average it actually. So that is the response. Okay, so that's basically like sum of product operation divided by the number of elements, like so how many elements you are trying to take. Okay. So if I perform the convolution operation, this is the output you get it. So if I try to perform the convolution operation with 3 filter maps, feature maps. So these are the 3 feature maps. Okay, so these are the kind of response, 3 response images you get it. Okay, so this 3 feature maps or the feature maps is combined into one group. So that forms one convolution layer. Okay, so basically, so this is to just to show you that how does the convolution layer looks like. in like, okay, so you probably might have used ResNet or different type of networks probably will be using, right? So inside, so this is how it looks like. Okay, so basically it will have like number of feature maps, and you are trying to perform the convolution operations. And Depending on the number of feature maps inside each layer, you will get so many number of responses. Okay. So now for this particular image, if I have 3 feature maps, so these are the 3 responses you obtained. I'm just, okay. So now if you want to perform a pooling operations, so usually you can select 2 by 2 or 3 by 3, whatever the size. Okay. Now we consider 2 by 2 with the maximum pooling. So within this area, okay, 2 by 2 area, I am trying to take the maximum representative from this. So same thing here. So this is the response after performing a maximum pooling operation. And same thing will be performed for all the feature maps. Now, if you are having a pooling layer, convolution followed by pooling layer, and this is what the output you get it. Okay. So in the previous case, we had like with one convolution layer with 3 filter banks. Okay. And so maximum pool layer with 2 by 2 and stride is equal to 2. This is the response what you obtain. Clear? So sometimes we want to perform the normalization. So just to ensure that okay, so the all image intensities are in the same range. So here we have used like okay, so kind of rectified ReLU as a function. So basically like ReLU is a kind of activation function where you try to suppress all the negative values and keep your positive values as it is. Okay. You can use, you have a flexibility to use whatever the kind of activation function you can use. Okay, here if I use ReLU, so you can see like okay, so wherever there is a negative, it will be turned off, and remaining thing like so it will be same. And this is the output of ReLU layer. Now if you perform this ReLU for all the output, so you will get. So now what we did, this is my input. We have one convolution, ReLU and pooling. Okay, and if I perform these operations, this is what the output you get it. See, sometimes for some architecture, all these two will be embedded inside this, okay, or like okay, you can separately specify this, and you have the flexibility. Like okay, so when you are using Cafe or like okay, so even PyTorch or TensorFlow, you have a flexibility to define whether you want to have these kind of layers at every layer, or you can omit or you can add. See, I think probably if you have used, if you are constructing your own architecture, probably you might have experienced this. Or sometimes like, so if somebody is directly taking some pre-trained architecture or pre-trained model, so probably you might have not experienced this actually. So there is, as I already said, nothing wrong or nothing harm in using pre-trained model, at least just for the sake of understanding how it works, at least try to do some experiment. So what happens if I change something instead of ReLU, if I use like okay, so some other activation function, what will be the response? If I instead of max pooling 2 by 2, 3 by 3, if I use 3 by 3, or like so instead of max pooling, average pooling, what happens? At least that will give a different perspective. Clear? Now, so deep stacking means because deep learning talks about the modularity. So you will have like, you can have any number of such layers, you can stack it. Okay, so you will have like input image, so convolution ReLU, so pooling. So this you can interchange and you have complete flexibility to design your own architecture. Okay. I think probably, how many of you are familiar with NAS? Neural architecture search. So basically neural architecture search basically perform this kind of experiment for you. Okay, as part of your AutoML, see, I have a data set. I don't know which architecture to select. I want it to perform. So you need not even worry that. So even like, so there is a tools are already available, so which helps you in doing this. So you use AutoML or like, so NAS, which will try to suggest a best possible architecture for your data set to meeting your end objective. Okay. Clear? So now, if I use this kind of architecture, so So convolution followed by ReLU, convolution, ReLU, pooling, convolution, ReLU, pooling. So ideally, I end up with this kind of feature map. Now, if I feel, okay, this is good enough representation of my data, what you can do is, you can consider this as a feature map, final feature map, just perform the flattening operation. Flattening is just try to arrange this in a linear vector by concatenating like so different feature maps. So this is how you get it. Okay. Now, if you feel this feature vector is good enough, I will use this for clustering, take this and perform the clustering operation. So as we discussed about for the auto labeling. Anyway, why? This is not some random numbers. These are a refined representation of your data. You can still use this as a feature vector and use it for the clustering. So if you use this and perform the clustering, so you are already performing a clustering of the images without even straining much on like extracting the features and etc. and so forth. Or you feel like, okay, so I will take this feature vector and I still perform like instead of neural network, I will try to perform k-means or SVM or any other classifier, or you want to reduce the dimension, you can still do that. So you have flexibility to do that. Or if not, you want to bring it into a single framework of deep learning. So take this feature vector, I have a fully connected network, FCN layer, and perform the classification. Finally, like, okay, we'll have a one FCN followed by a softmax layer to perform the classification. Clear? So you take any architecture. Internally, there could be like so slightly different in like so how many number of feature maps or the filter banks they are using, or how they are combining the pooling, but the working principle is same. Understand this. So once you get into this level of details, even if you want to customize some of the architectures, okay, for example, Google Net you want to take and you want to customize, you can do that. You want to take ResNet and you want to customize, you can always do that. For that, you should have this level of understanding. How does it work? What individual layer and individual element, what it is actually doing. So once you have that kind of understanding, you can always play around that architectures. Clear? Any questions? No? Well, so then if you perform this operation, so of course, like so you already know like how does the neural network works, right? And if I take this input vector, so now like this forms as an input vector, and then like we say we'll have one hidden layer and then output layer, and this is what the response you get it. So it says it's a X with confidence 0.92. That's it. You built a classifier to classify X and O. This could be phase, non-phase. It could be tumor, non-tumor. Or it could be OK product, NG product, anything. So whatever the problem, so your way of building the architecture or the deep learning model relates like this. Clear? Of course, we didn't talk about the learning type. So learning, I think probably already you know like so the back propagation and how the learning will happen, right? So in the similar way, here also you try to learn. So only thing the difference between the traditional neural network training and the deep learning or the CNN training is, in case of CNN, I am not learning about the edge weights, rather than we are learning the filter bank weights or the feature map weights. That's it. Clear? Any questions? So we talked about this one, right? The architecture, like so deep stacking. So what are the problems one can encounter in the process of building this architecture? Of course, one is to deciding like okay, how many layers, how many filter banks. Okay, that is one. So if you decide all these things, so once you start doing this, there is no limit on adding number of layers, right? You can keep on adding it. Is it okay to do that, or do you see any problem with that? What problem it can happen? Hmm? Complexity increases. Okay. I have a Azure AWS cloud, Azure cloud. I don't worry about the computation. I have unlimited computational bandwidth. I have good GPU, and I don't worry about the time. Inferencing, okay. Assume that, okay, so then I think probably you might be knowing, right? Like, so NVIDIA comes with TensorRT engine, like, so which will optimize your model to specific hardware. Then, do you see any problem with the training process itself? Hmm? Okay, can anyone explain me, like, okay, so what is the backpropagation, how the learning happens in a neural network? So typically, assume that, okay, these are the FC layers or a traditional hidden layers of a traditional neural network. So yeah, some error here. How do you adjust the weights? So you take this. So this error is because of what? So now, like, okay, so I am at the output layer. I expect output as 1. I got, this is my desired output. Okay, so I got 0.97. This is actual output. What you do? Of course, you compute the error. Error is correct. So absolute output, the desired output versus absolute output is your error. You got some error. Error is this 0.03 is the error is because of what? Weight of, okay, so you have an output layer here. Because of this? Of course, yes, because of this only. This has got how many component? You have like, okay, weights from the previous plus activation function plus bias. Okay, assume that I removed the bias. So this error 0.03, either it is because of the weight here or because of this activation function or because of this. Agree? This is how you try to propagate back, right? So now you try to compensate. How much is because of this? That's why you try to perform the partial derivative. And then you try to factor it. How much is because of this and how much of because of this. You try to adjust it. Here, you try to adjust this and then you go back. So now you have one more hidden layer. So here, the error because of this, it could be 0.0002. Because there are so many other layers, right? I'm just trying to take like 0.002. If you partially derive, like probably like so the contribution of this error because of this could be this much. And again, this may be another hidden layer, right? If you try to propagate back, it could be 0.000001. Propagate back. After some time, what happens? This becomes so small, nothing will change. What is this? It's a vanishing gradient problem. That means, okay, so just for your convenience, like okay, it's easiness of usage, you added so many number of layers. But actually, you try to do the experiment, I'm trying to add more images. It is not learning, nothing is changing. What is happening? Internally, after certain layers, nothing is getting changed. That means all those layers are becoming almost dummy. Nothing is, it is not even contributing anything because of the problem of vanishing gradient. That means not only stacking, like so if you keep on stacking, so just because like so some feature, like so some tool is performing or giving this kind of opportunity or like so facility, just don't blindly add it. Try to see whether gradients are percolating back and it is percolating to the very first layer. If that is not happening, so then your whole process of training doesn't make any sense because nothing is getting updated at the initial stages of the network. Right. What else can happen? Reverse of this can also happen. Exploding gradients. So that is another problem. Okay. So that means what I am trying to convey here is, don't blindly do experiment like, okay, so yes, I have given the image. My experiment is what? My expectation is 99%. My guide has told, like, okay, I need to generate 99% result. Without that, you won't clear. Okay, I added 1 layer, 2 layer. Okay, after 2 layers, oh, from 70 it is increased to 75. Okay, let me keep on adding it. So then you keep on adding it, like after some time, like nothing is changing. Then you don't even get into analyzing what is the problem. Then you will say, this is the maximum I can achieve. Problem could be because of your data. Problem is because of this, the type of feature bank you have used. Or problem is because of your exploding or the vanishing gradients. Always, as a researchers, try to get into that level and try to see, like, so whether what actually happening. Even before trying alternate approach. See, this is another problem with the researchers, and especially like, okay, so the deep learning engineers or the deep learning people who are working in the deep learning is, so they try, everything is available. Like, I will try to find, okay, 1, 2, 3, 4, 5. That you need not to do it. I already have like this automated method to get that one. So when I say like, so you are a deep learning or the machine learning engineer, the expectation is at least to see, okay, I got 90%. Why 90%? So my model is missing 10%. Where it is missing? What kind of images are getting misclassified? Why it is getting misclassified? Is it because of like so less number of samples of that representative data? Or why my model is not able to learn this kind of 10% of data? At least that level of analysis you should do it. That is a bare minimum thing. When you do that, I am sure like you will come up with some other solution to tackle that problem. Unfortunately, why that is not happening? Because you don't even get into that level. Okay, I got 90%, so I added the additional layer or the data, nothing is changing. Okay, let me change other architecture. So I got 92%. So you don't even get into analyzing like, so this previous model got 90% and this is giving 92%. What is the problem? Whether it is 2% is missing, what kind of 2% is missing? Whether it is the same kind of images are missing or different type of images. At least if you do that kind of analysis, at least you can think of fusing these two classifiers to improve the overall result. You don't do that. Why? Okay. So please don't do any experiment or don't do any result generation blindly. Clear? Okay. So all of you are able to understand like how the how to construct a deep learning architecture, right? And this is true for most of your architecture. Whatever the type of architecture you take, I think it is more or less in the similar. It's in line. Yes, sir. Okay, so I think again there are some standard network. I didn't cover everything. So very early stage network for the CNNs. So one of the earliest network is LENET. So basically like this works for grayscale 32 by 32 image, and these are the number of feature maps. So it has got 6 feature map, like okay, so it will generate 28 by 28 output image. Okay, how? So basically it will try to perform so many number of convolution, like so probably you can see 3 by 3 or 5 by 5 convolution. So it results with 28 by 28. And second, this is the softmax operation. So which will reduce this 28 by 28 with 14 by 14. So with 2 by 2 max pooling operation. And in the third convolution layer, you'll have like 16 feature maps. Okay, so it will generate 10 by 10 image. So just to give you like glimpse like how they constructed it. So basically, the overall process, like whatever we constructed, right? It's exactly in the similar line, but the number of features and feature maps they have used is different. Clear? So finally, like if you use LENET, the number of feature map it will generate, final feature map it generates is about 120. Okay. So you'll have like so fully connected layer with 28 for neurons, and output is 10 because it is basically used for handwritten numeral recognition. Okay. So number of learnable parameters or the trainable parameters is about 60,000 in case of LeNet. So this is AlexNet. So here like so this works for 224 by 224 image. So this is the construction of. So just try to see like so it's exactly the similar, like so we'll have like convolution for max pooling, convolution max pooling, convolution max pooling, dense layer, and the output class. Okay. So this is VGGNet. Again like okay, so it's exactly in the similar input, followed by 3x3 convolution with 64 filter banks of the feature maps. Again followed by one more convolution with 3x3 with 64. So 2 convolutions, then pooling, 2 convolutions, pooling, 2 convolutions, pooling, etc. and so forth. This is ResNet. Okay. So ResNet basically to avoid this the vanishing gradient. So they are like this is some kind of sorting kind of operation. So which will try to transmit part of output input directly to the adjacent layers. So original ResNet was having 152 layers. So we have variants of ResNet 50, and we did a lot of experiment, and we found like so ResNet 14 or ResNet 18 is good enough to solve most of the classification problem, especially for defect classification. We consider different type of products, and for most of our cases ResNet 14 or ResNet 18 is good enough. I think we trained about one of the complex product is about 512 different type of defects. Okay, and so we trained about billions of images, and we could able to achieve almost 100% classification accuracy with less than 0.1% of missing rate. So with ResNet 18, that means so you need not to consider like such a deep layer. So ResNet 152 is basically built for a very sophisticated application, but ResNet is a very good network if you are working on images like okay, so for the image classification kind of thing. So ResNet 14 or 18 is still good enough. Okay, so some of the tips if you are using a while training the deep networks. So when you are trying to make a different experimentation, try to do the experimentation with respect to different activation functions. Okay, so don't try to look for only one type of activation function. So we have like ReLU, leaky ReLU, or different type of activation function. Try to study with different activation functions. So also try to learn with experiment with learning rate. Okay, so fixed versus dynamic. So I think probably you know the impact of learning rate, right, or the effect of learning rate. Okay. So what happens if you are having higher learning rate? Okay. Okay. So which one do you use? Like okay, so why not very slow learning? Okay. So what is the value you will use? Okay. So on contrary to this, of course, like because of the larger learning rate, so there could be a like oscillation in the solution, optimization, and because of that, probably it may sometimes miss your actual local minima or the local minima. Okay, when you are trying to find that minimum point. Okay. On the other hand, if you use very small learning rate, okay, the thing is it takes too much of time to converge. So that's what like so most of the time fixed learning rate works, a small fixed learning rate works well if your data set is small, and if you are working on a very large data set, so better to go with a dynamic approach. So the dynamic approach is basically you try to make this learning rate as a function of the epochs. right? So initially you start with higher learning rate, allow it to go near to your solution, and once the number of epochs increases, right, you try to divide. Okay, so initially let us say I start with 0.25 as a learning rate. So when the epoch is 1, I try to take learning rate as 0.25. So when the epoch becomes 2, it becomes 0.125. When it becomes 3, 4, so as the number of epochs increases, this becomes smaller and smaller. So still it ensures that, okay, so you will not miss your local. So this way you can balance both, like not missing your local minima, at the same time you don't take too much of time to optimize the function. Okay, and again, like so we have different instead of the standard gradient descent, we have like adaptive gradient descent algorithm, ADA delta. Like so, these are the different type of learning algorithms you can use. And of course, like because another problem with most of the time is the regularization. You end up like you trained your network, and you are unable to decide whether your network is overfit or underfit. Okay, because you don't get into that level of analysis. Okay, try to do the analysis and try to see whether your model is overfitting the data. If it is overfitting, try to reduce some of the parameters with the help of dropout technique. Like so, you can randomly drop out some parameters and try to see like so whether your solutions are like you are moving out of the overfitting. So how do you decide like so whether your model is overfit or underfit? What kind of test you will try to do? Graph with the loss. Okay. What it will say? So what is in the x-axis? What is the parameter in x-axis? Okay. So what? What do you say about this graph? Can I say like okay, so this is overfit or underfit in this case? Okay, what kind of test like so probably all of you are using it, right? So what kind of test you will try to do like okay, so to ensure that okay your model is overfitting or underfitting? Okay, training loss versus validation loss. Okay. So that is training loss is very less and validation loss is high. So then, what is that scenario? So, any other? That is the only test you try to do. So what is that deviation and bias like we will try to see? What is the factor? Okay, what kind of action you try to do if it is underfit? Variance and bias. Okay, so variance and bias, right? Okay, so what factor of variance you will try to take to say it is a overfit or underfit? So basically, like you always try to take your training versus validation loss. Okay, and if your training loss is very low and the validation loss or your test loss are like okay, so high, so basically it confirms that okay your model is overfit. Now if it is a overfit, what kind of action you will try to take? Okay, one is dropout or like you will try to see. Okay, then you try to redo the operation and try to see like so whether it is improving or not. What kind of action you will try to do if it is opposite? Your model is underfit. That means this itself is not going down. Okay, as the epochs increases, like so it will go down, like so then it stays at some level. What can be done like so? What is the action you try to do if it is a underfit? basically like for the overfit, obviously regularization is the one you try to incorporate. So you can have a different regularization method to overcome the overfitting problem. What kind of action you will try to do if it is an underfit problem? What is the meaning of underfit? Basically, underfit is like, so your whatever the architecture or the model you are trying to use is not able to fit your data, right? So that is the, so now what are the actions actually? Like, so whether you will remove some data or add data, or like, so increase the model, increase the parameters. Increasing the training data, so whether it really helps. More epochs. Okay, even if you increase the epochs, if it is not changing means. So basically, like, see, very like, okay, so very fundamental problem, like, so very at the very basic level, what it says, like, okay, so basically your data is so complex, your model is not able to fit it. So that's what, like, so you are trying to tell, like, underfitting means. So that means your data complexity is so high, and you have taken so architecture or the model which is having less number of parameters, not able to adapt or not able to learn all the variations. Obviously, you need to increase the number of parameters. How do you increase? See, it's opposite, right? Like in case of dropout, what you are basically you are trying to do in that dropout. Dropout is one approach, but in case of regularization, what you are trying to do? Basically, you are trying to remove like so some of the parameters here, right? Trainable parameters. So, in case of underfit, it should be reverse, right? How do you increase the number of parameters? Increasing the nodes, or increasing like so the number of filter banks, or etc., or like so changing the architecture which can accommodate. Okay, clear? That's what, like, so because see that is the simplest thing to do, right? See, I used LenNet, so it is not fitting. Okay, so I will use the AlexNet. So you even without you don't even analyze like so whether it is underfit or overfit. Okay. Any questions? No. So these are some of the advantages of CNN. So basically, like this is true for even neural network. So it assists transfer learning. So transfer learning means like so weight adoption can be possible with without training explicitly retraining entire thing from the additional data. So whatever the new data you are having, you can just try to have that new data, and you can start training from the already learned weight. So that way weight adoption can happen. So which encompasses or like so try to learn this transfer learning. So fine tuning of CNN is possible by keeping some early layers as it is and removing some of the last layers. So basically what fine tuning means, so basically I trained a neural network or the CNN for one application. How best I can do it for the domain adoption or the newer problem is, so you can still keep the early layers as it is. Why? Because in most of the CNN, like so the first few layers is trying to dealt with like so extracting the low level features, so which may be required for most of the problems. So that way you need not to worry about that the early layers. Just try to change the final layers and the FC layers, so you can still try to domain adapt it to different problems. You can adapt your network to solve the different problems. Okay, so fine tuning the later layers, like so that's part of your fine tuning, and you can use CNN as a feature extractor. I think probably we already discussed, right? Remove last fully connected layers. So you can use like only these features which can be used for your clustering or any other operations. You can still use it. Okay. So which can be used even as a like descriptor of the feature or the representation mapping, like that can be used. Okay. Okay. Any questions before we move on to the next topic? So all of you are familiar with like, so now at least you understood like how does the CNN works, right? Okay. Sparsity means like, okay, so basically like these fully connected layers, right? Like, so whatever you try to get this feature representation from this layer. So this layer contains like, okay, so too many zero values or non-representative values actually. Like, so that will make too many values for your fully connected layers, and like, okay, so and rest of the layers, like, so it is having so many number of map is not required, but still like, okay, so your fully connected layer becomes so deep actually, or so dense, okay, because of the sparsity. So in order to reduce the sparsity here, you can have like, so dropout and regularization in these layers, so that like, so you can control so the number of parameters which can go there actually. So the sparsity mainly happens like, so because you are having too many number of feature maps and too many parameters in the intermediate layer, and because of this, so you will have like more number of parameters here, and so it's not able to, it's not really required. It is not even not actually contributing to the actual classification. Any other? No? Okay, so if no question, I think probably we'll break at this point for lunch, and then once we come back, we'll quickly look into the few concept of auto encoders and detectors, and then finally we'll wind by touching upon like just looking into the kind of work we are trying to do in Samsung. And if you have any specific problem that need to be discussed, we'll try to take and discuss. Okay. Okay, thank you.
ತೆರೆ ಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ದಿನಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಜ್ಞಾನದೇ ಗುಲವೇ ಬೀಡು ಬಿಟ್ಟಿದೆ ಕಡಲಿನ ತಡಿಯಲ್ಲಿ ಅರಿವು ಮೂಡಿಸುವ ಗುರುವೇ ದೇವರು ನಮ್ಮ ಈ ಗುಡಿಯಲ್ಲಿ ಎಲ್ಲ ಸಾಧನೆಯ ಮುಟ್ಟು ಮೆಟ್ಟಿಲು ಹತ್ತುವುದಿಲ್ಲೇ ಮೊದಲು ವಿದ್ಯೆಯೇ ನಮ್ಮಯ ಹಕ್ಕು ನಾಳೆಯ ದಿಕ್ಕು ಜೀವನದ ಸೆಲೆಯು
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು
ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಜ್ಞಾನದೇಗುಲವೇ ಬೀಡು ಬಿಟ್ಟಿದೆ ಕಡಲಿನ ತಡಿಯಲ್ಲಿ ಅರಿವು ಮೂಡಿಸುವ ಗುರುವೇ ದೇವರು ನಮ್ಮ ಈ ಗುಡಿಯಲ್ಲಿ ಎಲ್ಲ ಸಾಧನೆಯ ಮುಟ್ಟು ಮೆಟ್ಟಿಲು ಹತ್ತುವುದಿಲ್ಲೇ ಮೊದಲು ವಿದ್ಯೆಯೇ ನಮ್ಮಯ ಹಕ್ಕು ನಾಳೆಯ ದಿಕ್ಕು ಜೀವನದ ಸೆಲೆಯು
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಜ್ಞಾನದೇ ಗೊಲವೆ ಬೀಡು ಬಿಟ್ಟಿದೆ ಕಡಲಿನ ತಡಿಯಲ್ಲಿ ಅರಿವು ಮೂಡಿಸುವ ಗುರುವೆ ದೇವರು ನಮ್ಮ ಈ ಗುಡಿಯಲ್ಲಿ ಎಲ್ಲ ಸಾಧನೆಯ ಮುಟ್ಟು ಮೆಟ್ಟಿಲು ಹತ್ತುವುದಿಲ್ಲೆ ಮೊದಲು ವಿದ್ಯೆಯೇ ನಮ್ಮಯ ಹಕ್ಕು ನಾಳೆಯ ದಿಕ್ಕು ಜೀವನದ ಸೆಲೆಯು
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಜ್ಞಾನದೇ ಗೊಲವೇ ಬೀಡು ಬಿಟ್ಟಿದೆ ಕಡಲಿನ ತಡಿಯಲ್ಲಿ ಅರಿವು ಮೂಡಿಸುವ ಗುರುವೇ ದೇವರು ನಮ್ಮ ಈ ಗುಡಿಯಲ್ಲಿ ಎಲ್ಲ ಸಾಧನೆಯ ಮುಟ್ಟು ಮೆಟ್ಟಿಲು ಹತ್ತುವುದಿಲ್ಲೇ ಮೊದಲು ವಿದ್ಯೆಯೇ ನಮ್ಮಯ ಹಕ್ಕು ನಾಳೆಯ ದಿಕ್ಕು ಜೀವನದ ಸೆಲೆಯು
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಜ್ಞಾನದೇಗುಲವೇ ಬೀಡು ಬಿಟ್ಟಿದೆ ಕಡಲಿನ ತಡಿಯಲ್ಲಿ ಅರಿವು ಮೂಡಿಸುವ ಗುರುವೇ ದೇವರು ನಮ್ಮ ಈ ಗುಡಿಯಲ್ಲಿ ಎಲ್ಲ ಸಾಧನೆಯ ಮುಟ್ಟು ಮೆಟ್ಟಿಲು ಹತ್ತುವುದಿಲ್ಲೇ ಮೊದಲು ವಿದ್ಯೆಯೇ ನಮ್ಮಯ ಹಕ್ಕು ನಾಳೆಯ ದಿಕ್ಕು ಜೀವನದ ಸೆಲೆಯು
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಜ್ಞಾನದೇ ಗುಲವೇ ಬೀಡು ಬಿಟ್ಟಿದೆ ಕಡಲಿನ ತಡಿಯಲ್ಲಿ ಅರಿವು ಮೂಡಿಸುವ ಗುರುವೇ ದೇವರು ನಮ್ಮ ಈ ಗುಡಿಯಲ್ಲಿ ಎಲ್ಲ ಸಾಧನೆಯ ಮುಟ್ಟು ಮೆಟ್ಟಿಲು ಹತ್ತುವುದಿಲ್ಲೇ ಮೊದಲು ವಿದ್ಯೆಯೇ ನಮ್ಮಯ ಹಕ್ಕು ನಾಳೆಯ ದಿಕ್ಕು ಜೀವನದ ಸೆಲೆಯು
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು
ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
welcome back. How was the lunch? Good. So it's very difficult session, right? Yeah. Okay, let's make it more interesting. Yeah, so before hello. That's right. Okay. So in the morning session, we were discussing about few aspects of deep learning and how to construct a CNN, and we also understood uh, why deep learning is more popular. Like to the fat networks has a sound mathematical basis. Okay. So before we get into the new topic, so if you have any questions or any clarification you need with respect to the topics which we covered in the morning, so you can ask me. Otherwise, if you want to, yes, ma'am. Yeah. Yes, so for a text data, so you instead of CNN, you can directly use the FC network. So that is one way. Or like, okay, so there are one-dimensional signals. So probably like sensor data. So if that is the case, you can even still you can perform the one-dimension convolution. So both are possible. CNN, like, okay, unless you represent it as an image, so or like with a one-dimension CNN, so you cannot. One-dimension CNN, like for example, if it is a sensor data or a speech signal or even a text data, if you encode it as a one-dimension signal, you can perform one-dimension CNN. Or like, okay, so typically like the text image, like so whatever the text data you have, so if you convert it as an image, you can still perform the CNN. So that way you can. Two-dimension is what we consider, but it can be like, okay, so it is not, the technically it is not significantly different even if it is a one-dimension CNN or a three-dimension or any other dimension CNNs. So the approach remains still same. So only thing is like, okay, so instead of the perceptron, general perceptron operation, we are trying to perform the convolution operation. But if the data itself is a numerical form, if you want to, if you don't want to use CNN and you can still want to use deep learning, is you can still use it as a deep perceptron networks actually. So the nodes inside each perceptron, like so each layer will be performing the traditional perceptron operation. So that way. See, convolution operation, if you use like at the end of the your feature learning, it will convert it into numerical data only. So for example, before you give it to FCN, so whatever the data we get is numerical data only. This is what. Right. So now somehow you need to convert this text as a signal data. If at all you want to use the CNN. So one way of converting is like, so you can have like, okay, so the word vector format. So if this word vector, if you want to convert it as a signal, and if you want to apply the 1D CNN, you can still apply it. Or if you have like, instead of doing this CNN, if you have a word encoded format, so you can still perform DNN actually, instead of CNN operation. You are no longer performing a convolution operation, but rather than you are performing a perceptron operations. Anyway, like, okay, for the deep, these layers, right? So here we are not performing this, each node is not performing the CNN operation, rather than they are performing the perceptron operation. If it is convert it as a 1D or a 2D signal, then you can perform convolution operations. Any other questions? Okay, so if no question, probably we will move on to the next topic. I think probably today, these days, we are hearing a lot about generative models, right? So towards generative model, like so very first work with respect to the generative model was with respect to the autoencoders. So basically, this is a generative model where in case of a traditional classifier or a clustering operation, so you give a input as a numerical data, the image data, and ultimately like your output is a categorical type, like so whether it is a defect or non-defect, or if you are trying to perform the prediction, it will try to predict it. Okay? But there are some cases where I need to generate image as a output. So I give image as a input and I need to generate image itself as a output. So how are we going to generate that? Okay. So to do that, before we get into that generative model, let us try to understand what is this autoencoders and how convolutional autoencoders can be used to generate the images. Yeah, one of the very the simple. Okay, so the contents are jumbled. Okay, let us don't worry about that one. I will try to make this concept very simple. So what we try to do in case of this autoencoder is, so I have a signal f of x, so which is nothing but your input image or any input signal. Okay, so what we need to do is like, okay, so I need to perform certain operation on this f of x. Okay, so that I will transform this data into another form like s of wx plus b. So which is nothing but like an intermediate representation. I am trying to encode the signal in a format, so which is somewhat different from the input signal itself. Okay, and it results in something called z. So we call this z as a latent representation. Basically, I am trying to represent this f of x in a form other than like so different form, some z. My objective is, given this z, okay, which is a intermediate representation or a latent representation, how I can still able to generate this f of x or exact f of x, if not exact f of x, at least the close representative of f of x, how I can generate. That's the problem. Okay. So here, so how do you train your classifier? So when you train the classifier, so you give data x and you also give corresponding label L. What is expected as output? No, so given a input data and label, so you try to build some model M. So using this, and once this model M is generated, given x, you expect this label to be generated. Okay, and these labels are usually a categorical type. Okay, OK, RNG, or like so whatever the. Now, I am slightly changing my format in the way. So I give a signal x or a input x. Okay, and I take this x and try to represent it as some other z. Okay, and what I need to do is, given this z, so somehow I need to go back to x, if not x, some x dash from this z, so that the difference between zero. Getting me? So to take from x to z, I use some function f to generate this intermediate representation z. Given this z, I apply f inverse or other functions g, so that using this g, I should be able to get back to original. So that's all like this. So now this Z, whatever we are trying to do, it's a encoded format of X. Okay. And we are trying to call this entire process of from X to Z and Z back to X dash. It's a reconstruction problem. And so since my inputs and outputs are like while training, my input and output are exactly the same, we call it as a auto-encoded format, okay, or auto-encoders. Getting me? Is the concept clear? So what is the need of doing all these things? Say I give the X, and I am trying to generate the same X back, or something which is closest to X. Why at all I need to do it? See, in case of classifier, you know, like, okay, so you are training your model by giving some input and labels, so that you expect your model to be generalized. Once the model is generalized, you are trying to use that for the classification purpose. Here what we are trying to do it actually. What kind of problems you can solve with the help of this? Generating same kind of images. Why you want to generate the same kind of image? Hiding the information. Okay. Increase the sample size. Okay, we'll see like, okay, so what kind of problems can be solved. At least the concept is clear. So the concept is very simple, like, okay, so basically X is some signal, or like, okay, it could be your even numerical data, like, okay, so some height, weight, etc. something in terms of the feature. I take this, apply some transformation to get Z, which is an intermediate representation, and from this I am trying to generate another vector, so which is if this is X, so X dash, so the difference between them is expected to be negligible. That's it. Okay. So this here, like, so with respect to the terminologies, so generally we call it Z as a latent representation. So it is a, so this entire process of this h of x is equal to g of f of x, right? So this is an approximation function. Ideally, this h is expected to be zero identity function. So practically, like, so it is not always, like, so it gives that same x. So typically we call it as an approximation function. It is approximately equal to your input signal. Okay. If we do that, so what are the problems we can solve with the help of these autoencoders? Let us say, like, this is your input data. So input data has got 6 dimensions. What is the dimension of output? So since it's autoencoder, so since I expect same output, always like output dimension is exactly same. So if I call this as a x, this is x dash, what is this? What is this? Z, right? This is a latent representation. Now what I am trying to do, so I give x, get into this representation, intermediate representation, and this is my output. Okay, while training, how do you train your traditional neural networks? You train your traditional neural network, you start from here, generate this result. So here you try to compute the error, and so if the error is more, you propagate back to adjust. Now you are having 2 networks back to back. Agree? All of you agree? One network here to get this representation, and another network to start with this and generate this. Clear? Now, if there is any error, how do you compute the error? Error is between these 2. Okay, I am trying to compute this. If there is a error, I propagate back and then propagate back. I try to repeat this process till these approximations are acceptable or 0. Clear? Yes or no? Okay. Now, if you complete that training process, now we have a mechanism where if you give the data, it will give this representation, and if you give this representation, it will give back this. Now, if your data is 6 dimension, and if you are able to generate a intermediate representation of 3 dimension, what is this? So this is what compressed data, and this is typically what you do in the dimensionality reduction, right? So what is dimensionality reduction problem? You want to reduce the dimension, okay? So this dimensionality reduction, like so 3-dimension data is good enough to reconstruct your original data, unlike your PCA. So though where I can still perform the reduce the dimension, but there is no guarantee of reconstructing the data back, but autoencoders can reduce the dimension at the same time. If read, it will approximately reconstruct the data back. Clear? Okay. One of the application of autoencoders. So similarly, in some cases where you want to expand the data, I have a smaller dimension data, but I want to have a bigger representation or expanded representation of it. Okay, so I start with 6-dimension data, so where my intermediate representation is 8-dimension. So data expansion. Okay. Though like so which is not very popular way of representing. So can you name any application of this where like so I want to have sending videos? Yeah, this is compression is fine. This increasing super resolution. So basically I want to have enhanced representation. Basically like okay, so given this image, I want to have like so meaningful or the enhanced dimension or the resolution of the image. See? Problem is same. So that's the beauty of autoencoders actually. So why it is the generative model is like our generative AI is like becoming more and more promising or more and more popular these days. Conceptually very simple. So it's nothing more actually. Like so, though like okay, I am trying to explain it as a different term. So it is very simple. Like this. From input data, this I have one network. Okay. So where I am trying to give this as input, trying to generate some output representation, and I have another back-to-back another network. So where I start with this and go back to this. Okay. 2 networks back-to-back combined. So with the objective of matching input-output pair. So such kind of networks are called autoencoders. Okay. Autoencoders has wide variety of applications. So probably you can say like so this is a compression, data compression. It could be for any data, like okay, so not only for images, it could be of any type of data. You can use it for compression. So super resolution, like we want to enhance the data representation. So represent it. Clear? Which one? This and this? Network wise it is same. Architecture like okay, so probably like okay, the way you train it could be different, but architecture wise both are same. What is your purpose actually? Whether you want to reduce the dimension or whether you want to generate a super resolution image. Depending on that you can use either this or this kind of.
When we should have that compressed data, when we should have that enhanced data.
Okay. For example, like so that depends on your problem actually. For example, you have a problem like okay, where you need to transmit data over a network. You have a large set of images or the videos and you want to transmit the video over a network. That is your problem. So somehow you need to have like okay, so some kind of representation, a smaller representation, so that I know like okay, so what is my encoder model. So I use a F function to generate this encoder, this encoded information or the latent information at the source side, and I will give a function G to you or the receiver to reconstruct this data back. Okay. Now what you do like okay, so if I have thousands of videos, I just apply for F to to generate 1000 intermediate representation. This representation is far, far smaller than the original representation. Getting the point? See, I have like, okay, so let us say 1000 videos, each of let us say like 1 GB. So now I have one function f to generate this. What I will do, all these 1000 images, I give it to this function f, it will generate Z1, Z2, Z1000. Okay, the sender use this function f. For a receiver, what I will give, I will give G, and then I send this images. Let us say like after compression, this becomes like, okay, so instead of 1 GB, it becomes like, okay, so 100 MB or 0.1 GB. Okay, instead of sending like, okay, so 1000 GB of data, I am sending like, okay, so now 0.1 into 1000 GB of data, and it will be transmitted over network. And what this receiver will do, he apply this G on this to generate. So this is your original image, right? V1, V2, V1000. So now he is applying and get this. If not exactly, some A1 dash. Okay. So now what is the benefit you got? The benefit you got is, so you need very less bandwidth to transmit your data. Right? Okay, this is one problem. Like, okay, so if this is your problem, you select this kind of architecture. On the other hand, so somebody has captured the image of like, let us say like VGA resolution. I have like, okay, so thousands of VGA resolution image. Now somehow I need to convert this VGA resolution to HD resolution. Like let us say you are storing the data in a VGA resolution, and I want to stream this data, or I want to cast this data using HD resolution. So that's what like your TV networks would do, right? Like, so I have a low resolution video, and but my system or like so my television can support only HD resolution. Now what I will do, I take this low resolution video or the low resolution image and apply this kind of architecture to convert this VGA into high resolution, right? So depending on the need, you can use this. So why I am trying to show this under complete or over complete? So this auto encoders can be used for data compression or the data expansion. So what kind of compression, how much you can compress and how much you can expand, that all depends on like so your need and like so depending on so how much error you are tolerant, right? Based on that you can try to incorporate. Clear? So but what is the difference between these two? How they are different? So if you look into the architecture wise, so this is your input. We will have like, okay, so some layers, C1 or like, so let me not use C. It could be any hidden layer 1, hidden layer 2, hidden layer 3. So what is the purpose of this network? It takes the data, it will try to transform this data into appropriate form, and it will try to have like some kind of representation here. How do you decide like, okay, so what kind of transformation happen here? What decides at least like, okay, so what kind of data will be, if I collect some data from here, what will decide like, so how the data will be formed or transformed from year to year? Or which factor, assume that okay, it's a neural network, which factor decides if I give this input here, if I collect some output here, output of this layer, output whatever the output I collect from this layer, depends on what? Convolution operation, okay, it could be convolution or any other operation, right? So if it is a simple perceptron operation, what kind of weights, bias you used, decide. I am simply talking about, not talking about the convolution, I am simply talking about the perceptron model. So now if I take this numerical data, so if I get some data here, this data is because of what kind of weights and bias I used. See, for example, you have like, okay, so here like final classifier, a softmax layer with some output layer. If I put these two, obviously like, okay, so how do you train your network? So you try to collect like, okay, so what is the output here? So I expect 1, but I got 0.9. So you try to backtrack, okay, and try to adjust the weights, right? So depending on that, over a iteration, number of iteration, it eventually like, okay, if I give the same set of input, instead of giving 0.9, it may give like, clear? I am trying to iterate this process of back propagation till I get this result. Clear? Okay. Now what I am trying to do, I am just trying to remove this softmax and the output layer. What is my output in this case? My input is exactly the same as my input. What I expect through the autoencoder, I expect same output. Whatever the input I am passing here, I should get the same as the output. Clear? Okay. So this is what my H3. So in order to reconstruct it, I am trying to have another network. Like, so it is a opposite of whatever you try to perform here. I am trying to perform the operation output of opposite of that. So I will say like it is a H3 dash, or I will try to represent D or some G3 or like G2, G1, and finally input or the output. Now while training, what I am trying to do, I try to compare these two. If they are same, okay, they are in order. If not, propagate. I try to train in the exactly same way. How I train my neural network. In the exactly same way I will try to do it. Once this network is completely trained, that means whenever I give input, I expect same output. That means weights are in place, everything is. Then whatever this H3, I call this as a latent representation Z. Depending on this or this, I can decide like, so what should be my Z value. Now I have two networks, right? This is my first part of network, I call it as a F. This is my second set of network, I call it as a G. This is encoder, this is generator. Yes. 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 Okay. If you use F for the generator, what will happen? See, F you are trying to transform. So your input you are already transforming. G should be inverse of this F, right? Rather than FL. So G is, basically I am trying to use a different function, G. So G ideally is expected to be inverse of it. Now the problem is, so since it is a nonlinear function, whatever the transformation, for a nonlinear, the existence of inverse is not always guaranteed. So theoretically, yes, I agree. So you have F, so if it is a linear transformation like Fourier transformation, I can apply the inverse Fourier transformation. But the problem here is, my function is not linear. I think you are already agree, right? Neural networks are not linear function. So now, since I don't know what is that inverse of it, that's why I am using different function G. Ideally, what is the mathematically like what is G? The functionality of G is to get a inverse of this. So since these two are non-linear function, for a non-linear function, the inverse is not exist or not guaranteed. So that's why we are trying to. Clear? Look at the beauty now. I have one network, another network. I train exactly in the similar manner. So now you are ready with something called generator. I can encode, from the encoded data I can generate. So what can I do? These are the kind of, you can compress, you can decompress, you can enhance the resolution, etc. and so forth. Okay? And this forms the basis for your generative model. Okay? So here I am trying to generate some kind of data. In fact, before the GAN, generative adversarial networks, okay, so which popularly you use for generating the data, right? So mostly even GAN models were generated or originated based on this. Generative AI is like I want to generate something. See, basically in your classification, objective is not to generate something. The objective is what? To classify. So once you perform the classification, the task is end. But in the case of a generative AI, I want to generate something. If I give something, from that input, I need to generate something else. If it is generating exactly the same, we call it as autoencoder. From some data, I want to some other form of data I need to generate. So generally, like okay, we don't call it as autoencoder. We are trying to generate some other form of data. For example, I give an image. I want to generate a caption out of it. Output is not a classification. Input is image. I want to generate a caption. Okay, so if I give a picture of this all, so you should tell that okay, it's a classroom. Somebody is talking and like so students are participating. That is the kind of output I need. So it will generate, right? So the basis of generation is similar, or the basis for like we said all the generative model originates from here actually. How do you train such kind of like so we talk about transformers and other things like so to build this GPT models, right? But the basis originates from here. I think most of you are familiar with GPT models, right? What is GPT? Chat GPT. What is GPT stands for? Generative pre-trained. What is T? Transformers. Generative pre-trained transformers. So basically transformer models were generated. And how do I generate? Okay, so there is a huge pre-trained model. So generative pre-trained transformers. I need to transform my data into another form. Right? Clear? Any doubt with the autoencoders? So if you see autoencoders, autoencoders will not generate. Autoencoders, the limitation of autoencoders is it can generate the data exactly. Okay. So why like okay? So though like we are able to generate the images, using the autoencoders, so why GAN or generative adversarial networks are generated or the built is mainly because of the limitation with the GAN models, or sorry, autoencoders. Because autoencoders can generate only image matching input and output. See, for example, in GAN we give mask. I want to generate a segmentation mask actually, give an image. So those kind of like variations will not be captured from the autoencoders. So that's the reason like so we have a different generative models. But what you need to understand is how it all started with respect to the generation, data generation part. Okay, so this is how it. Clear? Any questions with respect to this model? So it is, if I put it in a very, very simplistic form, so it's a two networks back to back. So where is like, okay, so your G network is always opposition, like, okay, are the opposite of your F function. Okay. And this Z is the intermediate representation or the latent representation, so which can be used for like separating or the encoding your data. So it can be used for cryptography, it can be used for whatever the purpose. Like for example, you want to transmit some data, but I don't want in a secured manner. You can just transmit Z. So use function F to generate a latent representation, and so give only function G for a receiver to decode the information. Nobody else should be able to decode it. So it can be used for data compression. It can be used for like data expansion, super resolution image generation, etc. and so forth. In addition to that, you can do a lot of other things. Okay. So this is under complete. Okay, this is like if I talk about the convolution. Okay, so if you replace this intermediate layer by a convolution operation, you will have like convolution autoencoders actually. So what it does, so you have an input image, you have a sequence of convolution layers, and you will have some kind of data representation. You will have a reconstruction stage. So in case of a convolution neural network, given an image, you perform the convolution operation till like okay, you get a representation. In the opposite side, instead of convolution, you perform the deconvolution operations. So you just perform the deconvolution operations in the opposite manner, so you get a reconstructed image out. Right? So, but again, this autoencoder can be used for any type of data, as long as your input, output, you are trying to match. So generally we call it as an autoencoder. So it could be speech signal, it could be text, it could be numerical data, or it could be even images. Okay. And again, the intermediate layers can be of any form, like so whether you want to use a morphological layers, MNNs or CNNs, or like even your perceptron data. So typically like convolution autoencoders look something like this. So we will have an input 28 cross 28 by 1. So this is mainly for which I built it for MNIST data set. I think probably most of you are familiar, like okay, so MNIST is a 28 by 28 image of only one dimension grayscale image. So we used one convolution layer, okay, with 16 filters. So then max pooling, so with the 2 by 2. So we will have like so 14 by 14 6. So again convolution layer 2 with 8 filter banks, filter feature maps. So again max pooling, convolution, max pooling, and this is your intermediate representation, or the hidden encoded actually, like last layer. Now we are trying to perform the deconvolution operation. Okay, deconvolution operation is, so you try to perform opposite of this. Then, so wherever you are trying to do the max pooling, right? Max pooling, what you are trying to do? Down sampling. You are trying to reduce the size, right? So here we are trying to perform the upsampling. Deconvolution, upsampling, deconvolution, upsampling, match your input and output. Clear? So this is how like, this is one example. So same network, I try to use the same network. So here, I wanted to reconstruct the image, okay? So with 50 epochs, and these are like reconstructed images, okay? So what was my original input size? It's a 28 by 28. So my intermediate representation is the reconstruction error is about 12%. So the accuracy is about 88% accurately we are able to generate. Like, so there are few cases. So it is, so some information is missing, right? Smudging and other things. Otherwise it was able to reconstruct. Now like, okay, so if I, instead of transmitting this much of data, if I transmit, this data, I can still able to reconstruct these images like this. Okay, so this can be used as a image reconstruction, or the because again this representation is not exactly like, okay, so in the image representation some numbers. So unless like somebody knows what kind of G has to be applied, you won't be able to reconstruct this back. So it can be used as a like, okay, so data security purpose, like how best you can secure the data. So this is another same network. Okay. Same network. What I did is like, okay, so I trained by same data, and this is the noisy image it was given, and this is my input. I expect like this my output should be like, for the, when I give this is the expected output. That's how I trained. So now if these are the inference result. So if this is the image, noisy image, this is the corresponding output.
What is the difference for denoising that?
Can you apply any denoising approach to remove the noise, such a amount of noise, to generate this kind of result? You can use like, okay, so probably you need to do a lot of experiment, right, to decide what kind of convolution you need to use. But whatever the convolution you use, like, so if it is any traditional filters, right, so probably this will try to reconstruct or remove the noise only up to certain level. But if it is significantly corrupted by noise, it's very difficult to generate. Other words, like, so I'm not telling that, okay, the denoising filters are like, so whatever the denoising filters available is not inferior. My objective is same autoencoder architecture, I'm able to still use it for
Different kind of transcoder may be used for different images.
right. So same like same architecture. So I try to generate a different type of results out of it. So which can be used for image reconstruction, or like with the data security, or like so even to denoise the images. See what other things you can do it. See, if somebody is working on a image segmentation. So now what I will try to train. So I train the image like, so input image, and I expect what I want to expect the mask as output. Same architecture will try to. See, you want to generate what is that? Given a image, you want to generate the segmentation masks. So now when I try to train like, okay, so the image pair and the mask. Okay, so now once that is done, so autoencoders can be used as a segmentation models. Clear? So the concept is same, it can be used for different. So whenever there is a need for generating the equivalent images, probably like, so these kind of approaches will help you in generating that. Okay, so that's the beauty of autoencoders, and in fact autoencoders paved the first pivotal step towards the generative model section. Any questions with respect to autoencoders? Is the concept clear? Right? Yeah. G? Yeah. Yeah.
Instead of taking the inverse of this, can you do some other functions and generate some other images or some other information and use it for any other applications?
That means you apply F, generate this
It need not be
from Z.
instead of getting back the out input. So instead of getting back this, can you do some operation?
Yeah, that's what I meant, like, okay, so when you say the image segmentation, so here like, okay, my G is not to generate this image, original image back. So rather than mask image, I want to generate a mask out of it actually. So here my G will be different. Speech signal, like okay, basically like you have some speech signal, you try to perform like so. For example, like you want to modify the voice, let us say. Okay. So enhance the quality, or like so, or undersample, or like so you want to compress it. So apply the same thing. So that will the Z will form your intermediate representation, and you can use that for rest. Any data. Autoencoder, as long as like so your input output you are trying to match, right? The same type of output input, so you can still use this for any type of data. So that's the reason, like okay, so here what kind of function you will use, like what kind of the processing you will use, I think that defines. For example, if it is a numerical data, probably I will use perceptron operation. So same operation will be available in the G case, G side also. It can be used for text, signal, or like image, any type of data. Yeah. So anybody is working on encoder model? No? Yes. Yeah. Okay.
So I need to generate a mask for an image. So at that time, this G layer will be reduced the size of the image. So original image will be downsampled and coming to the Z layer. So how will we generate a mask that is equal to the size?
So basically, like okay. So here, your objective is not to stop at this point. Your objective is to generate both, right? See now, when you are trying to train your G, instead of driving it to generate this exact image, you can drive it to generate the masks here. Okay, so that means for your input image, you know, like okay, so what is the mask you need to generate? You try to map it for that. So that means when I try to update the weights, I am not updating like okay, so comparing the input output. I don't take the difference between input and output. Rather than, so for this input, whatever the mask I get, right? So that mask and this mask I will try to generate. Okay, so that's how you need. So it's purely not autoencoder. So it's a kind of autoencoder, or like so purely it could be encoder actually. Yes. If you stop at Z without G, yeah, right. This one.
Yeah, this one.
Hmm.
So can we use that Z part only?
Yeah, of course. You can, if you give this image X, you reduce the dimension. So now it doesn't look like an image, right? So it has some kind of representation. I don't know, like, okay, so what could be the representation? It depends on, so what kind of value I will get. Some numbers, some junk I will get it here actually. So now, if you ask whether this Z is a representation of this input, I would say yes. Now, if you ask, can you generate this image from this Z, then probably you need to have G.
No, if I'm not interested in image, or if the intention is to have the dimensionality reduction, I work on that dimensionality.
If it, okay, correct. If it is,
Let us say, because I'm looking on text, I'm trying to connect it to text data. Let us say I'll get the reduced representation for the text, and I want to use it for classification as a dimensionality reduction or
whatever it is, like so a smaller representation of data.
smaller representation.
Yes.
So text is obviously high dimension.
Correct.
Very high dimension, in fact. So I use this and get the Z, and then I use that Z itself as features for the.
Yes, quite possible. That means in your application, your objective is not to generate. Rather than I want to perform some classification, but my classification I cannot done with my huge amount of data. So somehow I want to have a reduced dimension of this data, and it should be a meaningful representation. I train this entire network, but after this I am not interested in this. I will just chop this. Whatever the data I get it, I will use this as a reduced representation or the reduced feature, whatever, just like a PCA. I perform the PCA, and whatever the data, training data, I will try to subject it for this Z. All this Z representation, I will take it and train the classifier or clustering or whatever it is. And so that I build the model. Now, whenever the new data comes, I perform the same operation. This I will give it, and then, so then for you, like, okay, so the G part is not required. Anyway, PCA, anyway, it doesn't guarantee you, like, it is not possible to reconstruct the data. At least here there is a possibility to reconstruct, but since your application end object is different, you need not to worry about this actually. Hmm. Right. Right, yes. Here there is a guarantee that, okay, so it's a meaningful representation of your data, and if you want, you can always reconstruct it back. So depending on your application, whether you want to reconstruct or not reconstruct it. So generally, autoencoders, so since by the nature itself, we want to generate the data back. Okay, but if that is not the end objective, you can stop at that point. Yes. In fact, like this, autoencoders are widely used for dimensional reduction or the feature reduction. So especially for the image data, so like where I want to significantly reduce the dimension and still it is a meaningful representation, so autoencoders can be widely used. Which one? See here, like, okay, so in a, here this is a encoding part and this is a decoding part. So why we say it is a autoencoder is because we are trying to have same kind of input-output mapping. So whereas in case of a segmentation, it's not an autoencoder, it is an encoder-decoder model actually. Because I'm not matching exact input rather than to the mask, right? So it becomes a encoder-decoder model. Encoder-decoder for the image captioning. Image captioning, see, theoretically yes, but how do you build this network, that you need to see it actually. So basically, you start with the image. Yeah. Image captioning, basically like even before getting into that one, the problem is you start with the image. What kind of caption you need to generate? Okay, so now you got intermediate representation or the latent representation. From there, how do you take it and what kind of captions you need to generate? How do you frame that as a encoder model? That's where it. So typically for image captioning, right? So they use like so the transformer kind of model actually. Right. So ideally encoder generally like because of its nature, right? So we expect at least the modality should be same.
When the given input is fixed and the output is the caption, that is called as?
Which one? Image is input is image.
Image. Output is that the caption of the
basically we expect text, right? So generally that's the image captioning approach actually. Image captioning is basically you try to generate a caption for an image. That means you want to describe the image. Whenever the image is given, you want to describe what is the content present in the image. So the problem is a image captioning problem. So where your input modality is a two-dimensional signal or a image and output is a text, so a stream of text model.
this network can be used for?
No, actually basically like at least encoders, decoder model, so you expect like so the modality should be matched. Okay, but not in the purest form, we cannot use that to generate a text caption.
You said 2 slides before, it's called as generative.
Segmentation for
Generative
GPT. GPT.
Generative AI you said.
Generative AI. So this is one way of generating the images. Like so basically, what it generates is like so for example, like if you give this kind of data, it is generating like so it's equivalent clear images. So it is basically trying to generate the data in a different form. Okay, that way it is a generative rather than like okay so performing only classification result. Okay, and So in order to classify it as a generative AI itself, so there are certain restrictions, as I already said, right? Like, so the modality should match, and like, so in its original form, autoencoders expect like, so input output should match. Okay? But however, these autoencoders, especially convolution autoencoders, paved the way for like, so these transformers and the rest of the generative AI models. Actually. So that's what.
No, I'm asking what is the name of that model? Given input as image and output as the caption, no? Some model is an AI model, some name like this.
Generative AI, so generative AI, like, so there are different, like even the DALE, like, so there are different generative models available to perform the captioning. DALE. DALE. DALE.
Can we use this for augmentation also? I mean, to increase the number of samples.
Basically, like.
Because when you say image, you may not get the exact input image. Then it will be slightly distorted. But slight changes will be there.
So you can use this as a data augmentation. So provided like, okay, you want to generate like, so you already have like, okay, very clear images, but so somehow like, okay, so you know like, okay, so the image capture, when you try to capture the images from the actual scenario, there could be some noise. You want to add that kind of noise.
Yeah.
So
Denoising, you are trying to remove the noise, but earlier
no.
one more slide. This one, this is conventional AI. Here we are generating the images, and
Right.
the generated images are not exactly the same as
Correct.
the given image, but similar we can.
Yeah, you can use this as augmentation, and even like, okay, so you just reverse it. So that means you have a clear images, but like, okay, so I know like, okay, so the noise will be added in the actual image scenario. You don't have those kind of images. You can generate these noisy images, and you can use that as a augmentation.
I mean, when it is image, you can have this arrangement.
Huh.
I mean, what can be if it is text data?
So same thing, like, so I said like, so the except for the convolution layer, so your rest of the things are exactly the same, right?
For example, I want to do the same operation for text data, denoising conventionally data.
Uh-huh.
I mean, if I use that as a text data,
Huh.
that's kind of.
Yeah, okay. This title, okay.
What may be the output after this auto?
How do you represent, like, so what, see, if you use this, okay, so let us see, like, how you are going to represent it first at the input layer?
I use the pre-trained models for that.
If you use a
I use the pre-trained because this has to be converted into numerical representation.
correct,
Yeah, I use the pre-trained models for
to convert it into numerical form. Okay, so then what is your auto encoder part, like, so that when you decode it, what do you expect actually?
I mean, according to this, I should encode, I should get some words.
So basically, like, okay, so now you want like, so some kind of jumbling of these words.
Some words as
So what is that, like, so the jumbling also, like, we will try to define it, right? See, how did I train this? Let us try to, like, okay, so understand the image case. How we trained this? So in the input size, I give this image, and like, so I no, like, so this is what I expect actually. Like, so when I give this one, so if I give this as a input image, and I expect this as a output. That is how it was trained. Okay, this is input, this is output. Okay, this is how I trained. So now, even for your text case, if you try to give this as a input, what you expect it as a output? That need to be defined, right? So if you try to define that, so then whatever the intermediate representation, then you will have, like, so that has already been captured. That should be, yeah, correct. Because even in the segmentation, when I trying to train the segmentation model, how I train actually, basically, like, I give this image, I want the mask. That's how I try to define it. Okay, when you try to do that one, so it will not qualify it as autoencoder, it is an encoder-decoder model. Because autoencoder by nature, like, it should be, the input output should be matched.
then that image caption will be encoder or decoder model.
No, image encoder, see, you,
When you input this image, out this caption is encoder decoder.
for in that case, you need to train, like, so many number of cases actually. The model will not be so simple. So for that, because if I give the same image for two different instances, or like image with smaller variation, so multiple captions can be generated, right? So that's the reason, like, so it requires much more deeper way of training. So that's where like your transformers and other things come into the picture, where like so training all possible data on all possible output, so comes into picture. Here like so it's a if it is a straightforward case, yes, encoder decoder model works. So which has a significant severe limitations on the type of problems or the kind of problems it can solve. So don't expect auto encoder in its original form, or even auto encoder decoder model in its original form will try to solve all generative AI problem. Okay, it has got a very significant limitation. But what I am trying to convey here, or what I am trying to propose here is, so how it all started with respect to the generative model. When they started, so probably like when transformer model was invented, or like so they envisaged, probably they might have encountered similar kind of problems. So which has got a similar severe limitations with the number of parameters it can handle. So that's how like so they come up with the transformer models, where like so it has got billions of parameters to train, learnable parameters. Survey. Maybe single article may not be the one single article may not. So it's all about like how do you read and connect the dots actually. But you should be able to get like okay, so some generative model, like okay, so any generative AI books, right? Probably it will try to give like okay, so some kind of links. A single survey paper may not be. Clear? Okay, so let us quickly look into object detection. So what time we need to wind up? 4? Okay.
Whether instant segmentation can be covered in this?
See, instant segmentation, there is a, nowadays I think probably if you are following in the segmentation, so SAM models, I think probably if you are following this, so there is a wonderful segmentation models, right? SAM, segment anything models, okay, which is very, so which is already pre-trained, and you give like any kind of data, it is at least like it is able to decently segment the images, more or less. SAM, SAM. SAM is segment anything model. DALE. This is for segmentation. SAM, segment anything model. So basically it will, for all type of image data, right? So it will able to segment actually. Like it's a pre-trained model without even retraining most of the time. Like so you can start using this as a base model for your data. Segment anything. DALE is for image generation. So it's, I think, I don't think like, so there is an abbreviation. It's a company name. So their model actually. So it is image generation. So we have used this for like, okay, so we have used DALE for some of our data generation in our company. The use case is, see, we were building video analytics models, especially for the fire and smoke detection. And mostly like, okay, we wanted this fire and smoke detection inside the factory, okay, where machines are under operation. So if it is an outside model, we can generate the data. Just you can set up a fire and you can collect the data. But when it is in the factory environment, it is very difficult to collect those kind of data. So we use this DALE, okay, so where you can specify the image or you can input the text, okay. So reverse of the image captioning. So here like, okay, you can, you will get a prompt. In the prompt you can tell that, okay, so I need to generate a fire and smoke image inside the factory environment, like so where the factory image represents, like, so you can give the reference image and it will generate a lot of images with that description. You can control like, so how many instances, like what should be the size, those kind of things you can prompt in the prompt you can enter, and based on the textual description, it will try to generate the data.
As I said, if it is in the prompt, if I give this wordings,
Hmm.
you get the images. So based on that, if any action occurs, it will generate.
So basically it will generate some images. So then you can keep on refining your results. Like, so I think all of you are familiar to use ChatGPT. Have anybody used ChatGPTs? I think so. It's the same. Like, so just in the prompt, you can start refining your results. So in the same way, in the prompt, you can just refine. So if you have a reference image, you can specify the reference image also. Based on that reference image, it will try to generate on top of it. In fact, like in Samsung, we are doing similar kind of project. Like, we are building a platform where user can generate different type of images. Like, so it's a platform where you can give a reference image and specify what kind of defects has to be embedded into those images. It will try to generate those kind of images. No, DAL is used for different purpose, like so that is for the image generation. We are building like a similar kind of platform, but not a what is that, prompting based. So it's a image to image based generation, image generation actually. I think probably you are familiar with OpenAI's GPT models. Right? I think this 3.5 free to use, anybody can use. 4 you need to pay and use it. OpenAI's GPT, ChatGPT. So this is basically like, okay, so any text, these are comes under the category of LLM, large language models. So large language models, LLMs. See, now the state of the art or the best solution, if you are asking, I think SAM is the.
Instance segmentation will find out exactly what is the difference between instance and sample.
See, SAM is an instant segmentation actually. SAM is an instant segmentation. I think the best result and free to use, I think you can use the SAM. I think it has been bench. Huh? UNet, you need to train actually. Like, okay, I don't think UNet has been trained for some application. It can be used for all other cases. SAM, confidently you can use, like at least for the 90% of the cases, irrespective of whether it is a medical image, whether it is a any kind of images, probably SAM can.
For advanced image processing, we can use SAM.
So, no, instance for the segmentation. So for the beauty is, so we wanted to study SAM for one of our problem. So which is, we capture the images using focus ion beam. Okay, so the images are captured in a different image modality, focus ion beam imaging. And we give that image and we wanted to segment like so the ceramic and electrode part. So it was able to reliably segment those kind of cases. So now if you ask like, at least to best of my knowledge, I think this could be the one of the best segmentation algorithm available, which can be readily used for different applications. You need not to retrain. UNet and other things, yes, it works for a specific domain, whatever it has been trained. See, for example, it has been trained for some medical application. You can use it for medical application. And to some extent, you may need to retrain it. So this, I am telling, like, so without even retraining, you can use it 90% of the time. Okay. I think object detection, I think mostly you are familiar, right? Like, so the problem is to detect the objects, okay, from the image. So here, like, so basically we need to identify the object and mark the presence of object using a bounding rectangle.
Sir, do you have any idea in PointNet, sir? As like PointNet.
PointNet, no, I am not used it actually. So why it is being used, like any?
For PointNet segmentation in drone scales, from drones equipped with radar. So
Drone? Later, okay.
to capture the images. So after capturing images in remote
No, we see for a similar kind of application, like okay, so even in Samsung, we are developing an LOS system. So this is non-line of sight system. So non-line of sight, basically like in the automotive applications. So what is currently available is like, so you have a mounted camera, like so from the camera you can see like so whatever the object, and whenever there is an object, it will try to detect and classify the object and estimate the distance. But sometimes, so you might have seen the crossroads, right? Yeah. Your vehicle is moving here and something suddenly comes from here. So your camera cannot see this because of the crossroads. Okay. So now what we are, the system what we are trying to build is like, so we have a two cameras mounted on the onboard and two radars. Okay. So now we need to cross calibrate between the camera and the radars and try to see like, so is there is any NLOS, like so it is outside the field of view of camera, but it is covered in the radar view, and try to so even for this NLOS we are using the SAM. Even for the radar data, it is able to segment it actually. But I never come across the at least we have not used any point net for that. Okay. So basically like the object detection, yeah, we are trying to do the classification of like first detect the object and then further classify like what type of object it is and mark with a bounding box. Okay. So typically what we try to do, like so it is a window, you need to move across and try to find whether there is a instance available. Okay, so this is how it will be done, and then like these are the candidates, and once the candidates are identified, you try to aggregate this candidate to define like so what is the maximum bounding box for this particular object. Candidate means like so whenever like see, this is your window. When you move it, see here also there is a presence of deer actually, part of the deer is present here or part of the cat is present here. Okay, and you get one candidate here, second candidate, third candidate, and all these candidates, because if you try to mark, okay, this is also cat, this is also cat, then it doesn't look good, right? So you need to mark one bounding box for this entire object. So that's where like we try to represent the object. Okay, so this is what like, okay, so this, which, so these are, see these are candidates, and some candidates could be false alarms. So you need to remove, you need to remove those false alarms. So then like, okay, so you try to see like, so which are the candidate, proper candidate, and based on that you need to derive it actually. So that's the basic principle of your object detection models. So for this, like, so we have very different approaches. So very first approach would be like, okay, so box proposal methods. So box proposal method means, so here these are all the boxes or the candidates. It says it's a cloud, or like, so this is object one, like that. So now you try to combine all these things into one group to say like, so what exactly the object is. Okay, so this is what the selective search or the box proposal method, where like so you are trying to search exhaustively, and within that you try to eliminate like, so which are all the objects or which are all the bounding boxes which are false alarms, and which are the boxes which actually represent a particular type of objects which you are searching. And then like, okay, so this I am talking about like, so the old approach. So nowadays like, so we have a much more powerful way of object detection, like in terms of YOLO models. Okay, so we are talking about YOLO 7. Okay, so this is RCNN, region proposal CNNs. So here like again you try to extract the CNN features to train like, so the patch wise, and try to see like, so what regions corresponding to what, like, so typically you will have an input image. You extract the regions, about 2000 proposals, and then here for each region you try to compute the CNN features and then classify it, whether it is this particular candidate is from a person or a aeroplane or a TV monitor, etc. and so forth. And if two adjacent box or the regions comes with the same person, same category, then you try to combine it actually. So this is how like this is the RNN works. And in fact your YOLO models are improvised versions on these kind of approaches actually. This is fast RCNN, like so typical. Which one? RNN is like, okay, so recurrent neural network, like, so that is mainly for use for the temporal data. So don't get confused with RNN and RCNN. Yeah, when it is represented with the CNN, R is regional proposal actually. So okay, not the recurrent neural networks. Okay, this is fast RCNN. So basically, here it is to reduce the number of CNN computation, like so how to selectively compute the CNN. Instead of computing at every stage, you try to compute and keep it at one stage and try to combine it actually. So reduce the, see basically like in case of a RCNN, every region, first you try to run your window and try to generate the candidates. So typically you will get about 2000 proposals, and for all these 2000 proposals you try to compute the CNN features in case of RCNN. So here, when you try to do this, where is that? Here there could be a chance that you try to compute RCNN for this, this and this, like if this is a bigger box, right? Here you may compute for one CNN for this and another for this. Instead of doing that, you compute the CNN feature for entire image and then you try to derive it actually within that window. So you need not to recompute like so for the overlapping regions and every regions. So that's what the fast RCNN. And in fact, your YOLO V8 try to follow the same approach. It will try to compute the CNN for one time and then it will try to perform the grouping the repropositions actually. Okay, so this is, you try to compute the RNN features or the CNN feature once and then you try to perform the combination actually. So based on the ROI features, you try to combine and then generate a region proposal. Okay. So this is again so some more improvement on the fast RCNN. So to reduce the region propositions. Yes, CNN anyway, like okay, so in all cases you are using CNN. The only difference between your RCNN and the fast RCNN and faster RCNN is how you are computing the CNN. Whether you are computing the CNN multiple times for each region proposals, or you are computing once and you are keeping. Yeah. Correct. See, in all cases, see basically like let us assume like okay, in case of a RCNN, you got 2000 you got like okay. Okay, so let us say like this is my image. I try to run the proposals now. So it says okay, this is a blank, this is blank, this is blank. There is something image. So now I got multiple proposals here and multiple proposals here. Now what you can do is like okay, so you compute like so this is one proposal. I will try to compute the CNN feature for this box. So it says like so then based on the CNN feature, I will try to see whether it's a background or the image. Okay, this says it's a background. Now there is another proposal here. I will try to compute. So then it also says it's a background. So since this is one background, this is another background, they are adjacent, I will try to combine this. This is how I try to do it. No, see, faster RCNN is how many times you are, in case of this, you are computing like, so now there is a, this is one region, right? This is another region. There is a 50% overlap. You compute the CNN once for this box. And this box, another time you compute. So 2 times you are computing the CNN. Instead of doing this, you compute the CNN for entire feature, entire box. One time CNN has been computed now. Now I have the computed and kept it. Now whenever there is a region, right, I will try to refer this and try to get whatever the feature represented, feature map of this. So using that feature map, I try to, so that way you need not to recompute the CNNs every time. Like in the RCNN case, you try to compute 2000 times the CNNs. Here, CNN is done only once. My proposals are still 2000. I computed CNN only once. So that way, like, okay, you work, because which is more computationally complex. Computing CNN is more computationally complex, right? So that's what we are trying to avoid with the faster and faster RCNN. Okay. So, yeah. How much I can take? I can stop. Okay. Okay, in that. Yeah. All right. I think so. Definitely, I won't be able to cover whatever I wanted to cover as part of Samsung company. I think probably in bits and pieces, I try to cover some places or like so give you the glimpse what we try to do it in Samsung. Probably I have some problems like this I captured like so. These are some trends I think. So this is extensively we work in Samsung electromechanics. So Samsung electromechanics is a group under Samsung Electronics, not electronics, Samsung group. So we pioneer in manufacturing the electronic components. Okay, especially like okay, so we whatever in Samsung R&D center in Bangalore, we develop solution to automate the manufacturing process. Okay, so all the manufacturing process like as I already said, right? If you take a handful of MLCC chip, it would be even billions of chips actually. It's so tiny. And some of the challenges we are trying to address is reduce the false alarms. At the same time, we don't want to have any miss. Okay, miss should be miss in the sense. So if there is a NG, we should 100% sure that okay we remove that NG. Okay, so that's what like miss has to be 0 and the false alarm should be as less as possible. And the amount of inspection like so that is one part. So where like your algorithm should be accurate. So look at like so there are other challenges we try to address. So we want to perform the inspection. So typically like okay, so we try to perform each MLCC chip has got 6 sites. 6 sites has to be inspected, and we inspect about 55,000 images in minute. So 55,000 into 6 is what the dimension of the data you get, and we try to perform those kind of inspection. Like so, that is the computation challenges what we try to handle it. In that aspect, we want our model to be highly optimized, not only for like from the highly optimized for the performance, memory, and the speed. Okay, and in addition to that, like in order to ensure that okay, these models are like continuously upgraded, and because over a period of time we are continuously manufacturing new type of products. Whenever we try to have a new kind of products, so the model behavior and model the data drift will happen. So we need to ensure that okay, model is up to date at any point of time. So that's where we try to bring in MLOps. These are the kind of work what we are trying to do in Samsung. And so now, like why I'm trying to give this as a trend in the industry automation is probably like you might have seen because people are telling like okay, so because of AI people are losing the job. Yes, to some extent I agree with that, but larger extent, so AI is throwing open like so different opportunity. All you need to do is like you need to upskill. Okay, you need to change the way of working. So now many industries are trying to adopt the AI technology to automate the process because otherwise they will be left behind. So in order to overcome that, like many industries are trying to adopt this automation. So there is a vast opportunity in the area of industry automation. So if at all, if some of you are working on a AI technology, of course, I am not asking you to deviate now. So, but always, as I already said, right? So don't blindly do some experiment or don't blindly do research. Try to question yourself. So because that learning is very, very important. You are working on a specific domain, we agree. But the underlying concepts, like probably like, okay, so today we talked about so many concepts, but the underlying concepts are always same. Okay, all you need to understand is the philosophy of that actually. In fact, like so if you are doing PhD, so PhD is not about solving your problem. Like nobody ask. I think I worked on partial object recognition. Shekhar sir worked on 3D object recognition. If you ask, are you really using your whatever the techniques you developed as part of your PhD? No. But what is important is what philosophy you learned through that process. That is what very, very important. Okay, always as part of your PhD, try to learn the philosophy, underlying basic principles, understand the philosophy of problem solving. That is more important. I think speech, you are already, like, so there is a lot of LLMs, okay, now prompt engineering, like, so different types of prompting. So this is also very good trend. Recommendation systems, I think it's already like matured enough. Like I still remember, like I was part of developing a recommendation system for Amazon back in 2010-11. Now it is so matured. Like so now, like so many systems or many retail investors are started adopting these recommendation systems. Okay. So this summarization. So we did like this again. So we did very interesting work in Samsung for data summarization. So one experiment what we did is we mostly like okay, we train the full article and we want to summarize. So that is the summary. So we did a inverse of this problem. So what we trained is like so we trained abstracts, introduction, everything separately. And I just when I give some topic. So I expect like, can you generate abstract? So can you like so based on that abstract, can you generate an introduction? Like so that's what like so basically we work the inverse of this summarization problem. So now people are trying to solve different type of problem. Like so this is very interesting application for the text summarization and even like video summarization or the image summarization. I think very interesting problems can be solved. So please look into this. So again in the marketing strategy. So what kind of strategies, what kind of trend, how do you combine the data coming from multiple sources to build a strategic plan for marketing? So very interesting problem like okay, so NLP and the LLMs. So conversational AIs, I think computer vision, I think probably like again in agriculture, like with precision agriculture and various other fields, yeah, lot of applications, automotive, and now like with EV vehicles and like so again a lot of emphasis on reducing the accidents and making the system fully autonomous. So a lot of opportunities are available in the area of. So some of the research problem, so probably like again it's not exhaustive. So some of the problems like I think probably you can consider models with limited data. I think probably morning we were discussing, right? So we know like okay, so the DL models will be good or the performance will be good when the data is more. How do you build a model like okay, where there is a data scarcity or like so less number of data? How do you still try to train the models like so with lesser number of data? Control level generative models, how do you control the generation? Like so if you are having a generative models, how do you control the generated results? Okay, so that's what like so controllable generative models. Uncertainty quantification. So whenever there is a uncertainty in the model, how do you quantify that uncertainty? Like so it's a basically part of your explainable AI. How do you interpret your result? So in the same way, whenever there is uncertainty in the result or uncertainty about the data, how do you quantify it? So that is also very interesting problem. So hybrid deep learning models, I think probably like again this already matured enough. I think TabNet probably if you are familiar, if you are using. So how do you combine the image data and text data together? Like so training both image and text data. Like so if you have image and also the caption, you want to train those images kind of thing, right? So nowadays like okay, we are talking about the TabNets. Okay, TabNet is if you are not expert, just try to look into it. So which takes tabular data as well as the image data to train together. Like so as a holistic method. Machine learning in safety critical systems. And AI in the edge computing. So this is going to be like okay, so another big revolution, because nowadays AI systems are available as a inferencing server in most of your handheld devices. Now, if you want to allow training to happen in these images, so then it is a whole lot of other challenge actually. Like, so that need to be looked in. I think again this is going to be another big revolution in the area of AI, especially for a low computing devices. Okay. Again, okay, so these are not exhaustive list. I just wanted to capture this. Okay. Which one? Fuzzy, yes. So there could be multiple approaches you need to bring in to solve this problem. Basically, like uncertainty quantification is, so whenever there is uncertainty, how do you quantify it? So I don't want the fuzziness again. I want to quantify it. Okay, so the quantification is what is very, very important. So which can be part of your explainability. Explainable, when we talk about the explainable AI, right? So how did I get this generate the result? Okay, so in the similar way, I want to quantify if there is any uncertainty. Okay. Okay, so thanks for your time, and it was nice interaction. So I had a great learning. Okay, so if you have any questions, probably we can discuss offline. Okay, you can always reach me in this email address. So with this, I thank you all for your patience listening and nice interaction. And at the same time, I take this opportunity to thank Shekhar sir and Shashilekha madam for giving me the opportunity to share my experience, the views in the area of deep learning. Okay, thank you all.
Okay. Dear participants, I sincerely thank Dr. R. Dinesh for his tireless effort in delivering as much as information possible to all of us. Even during the tea break and lunch break, he was busy discussing and clarifying participants' doubts. So, sir has addressed data drift, model drift, how to handle it, bridging the gap between uh, the feature selection and the classification, DNN, autoencoder, and object detection, and many more things. So, he made sure that our learning rate is optimal. It is neither high or low. If it is too high, then our brain will have skip connections and dropouts. So if it is too low, then we will have our brain will go to sleep mode, deep sleep. So I would like to say one kind of like understanding the wavelength of audience is also very important to have a effective lecture. Sir has estimated exact wavelength of audience by deep observation and given a very effective lecture. So on behalf of Department of Computer Science and all the participants, I would like to thank you, sir. Off the record, without mic, I want to say one thing. Sir's thesis that is titled as poor, but it is very rich in research as well as the documentation style. It was with me since 5 years. Just last week, I returned it back to sir's mentor. So now I would like to call upon Professor H.L. Shashireka Madam and also Professor B.S. Shekhar sir, my mentor, to present a memento to Dr. R. Dinesh sir as a token of gratitude. We will have a tea break now. We will assemble, come back after 30 minutes. Maybe now it is 4:15, right? So 4:45, we will have a participant presentation. Okay. That is article discussion. There is a group, volunteer. We have a volunteer group.
ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಜ್ಞಾನದೇ ಗೊಲವೆ ಬೀಡು ಬಿಟ್ಟಿದೆ ಕಡಲಿನ ತಡಿಯಲ್ಲಿ ಅರಿವು ಮೂಡಿಸುವ ಗುರುವೆ ದೇವರು ನಮ್ಮ ಈ ಗುಡಿಯಲ್ಲಿ ಎಲ್ಲ ಸಾಧನೆಯ ಮುಟ್ಟು ಮೆಟ್ಟಿಲು ಹತ್ತುವುದಿಲ್ಲೆ ಮೊದಲು ವಿದ್ಯೆಯೇ ನಮ್ಮಯ ಹಕ್ಕು ನಾಳೆಯ ದಿಕ್ಕು ಜೀವನದ ಸೆಲೆಯು
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋಕೆ ಈ
ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋತಿ ಬದುಕು
ಜ್ಞಾನದೇ ಗೊಲವೇ ಬೀಡು ಬಿಟ್ಟಿದೆ ಕಡಲಿನ ತಡಿಯಲ್ಲಿ ಅರಿವು ಮೂಡಿಸುವ ಗುರುವೇ ದೇವರು ನಮ್ಮ ಈ ಗುಡಿಯಲ್ಲಿ ಎಲ್ಲ ಸಾಧನೆಯ ಮುಟ್ಟು ಮೆಟ್ಟಿಲು ಹತ್ತೋದಿಲ್ಲೇ ಮೊದಲು ವಿದ್ಯೆಯೇ ನಮ್ಮಯ ಹಕ್ಕು ನಾಳೆಯ ದಿಕ್ಕು ಜೀವನದ ಸೆಲೆಯು
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋತಿ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ ತೆರೆಸುತ್ತ ಕಣ್ಣ ಈ ವಿದ್ಯೆ ಹೊನ್ನ ಕಿರಣ ದಿನ ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇನೆ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರ ದಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ನಮನ ನಮನ
ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋತಿ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋತಿ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋತಿ ಬದುಕು ಜ್ಞಾನವೇ ಬೆಳಕು ಬೆಳಗೋತಿ ಬದುಕು
ಎರೆಯುತ್ತ ಜ್ಞಾನ
Good evening all. The evening session we are starting with a participant presentation, and the first group to present is Team DOS, and the presenter is Mr. Manjunath Chetan.
Okay, good afternoon everyone. So today I'm going to present about a mutual bootstrapping model for automated skin lesson segmentation and classification. So it's a medical imaging concept where will be in this paper the author has been completely discussed with the skin cancers segmentation like melanoma diseases and all. So it is a high impact factor of paper which has been presented, in 2022, I think so. So it's an IEEE transaction of medical imaging. Impact factor is 10.6. So it has been published in this journal. So coming to the next one, agenda. So in agenda, I'll go with introduction, literature survey, challenges, methodology, results, conclusions, and future works. So automated skin lesson segmentation and classification are the two most essential and related tasks in the computer aided diagnostics in a skin cancer, where it is completely concentrate on segmentation and classification. Segmentation is nothing but to detect the localization boundaries in a lesion. Lesions is nothing but in English it's a wound where the cancer cells, in our skin. If you found any sort of wound, then we call it as a lesions in a classification to diagnose the type of them. So in this paper, they propose the mutual bootstrapping deep convolution network, neural network, which is in MBDCNN, which is a model for simultaneous skin lesion segmentation and classification. So they have used three things: coarse segmentation network, called as coarse SN, enhanced segmentation network, which is an enhanced SN, so mass guided classification network, which is mass CN. Both segmentation and classification networks are mutually transferred knowledge between each other and facilitate bootstrapping way. So this bootstrapping way is nothing but in a deep neural network which will be consisting of increment of the results capability between when we connect the two networks. Okay, also designed a novel rank loss and jointly used to, with a dice loss segmentation networks to address the issues caused by the class imbalance and hard easy pixel imbalance. So these are the thing where they have concentrated. So moving to the next slide, these are the challenges. The segmentation and classification are the challenges due to the three reasons. Low contrast between each lesion and its surrounding skin tissues results in a fuzzy lesion boundaries. So which we can easily see that, the first slide, the first image. So the skin and the wound is one and the same, looks like one and the same, so it's very difficult to identify. So inter-type skin lesion may share the visual similarities and intra-type lesions may have visual differences. So here inter-type is nothing but within the class, and intra is nothing but outside the class. The same class what I am speaking. The skin lesions is a very significant in a visual appearance, which may be corrupted by artifacts like hair, blood vessels, and air bubbles. I'll add one more things to this. The person who have a tattoo on in a hand or a shoulder, wherever you want. Okay, if the person have a cancer over there, so it is very difficult for a machine to identify that cell. So that's what I refer artifacts. Okay, coming to the next one. So you can see here blood vessels and air bubbles, just like hairs grown more in our hands or where the place has been wounded. So it is very difficult to identify the skin cancer when we come to it. So then the second image you can see in a water bubble on a skin where a wound is present, the cancer cell is present. It's also very difficult when we talk about deep neural networks. Any networks we can take, so it will be a little bit challenging for it. So literature survey has been divided in these things, methodology in traditional approaches and DCNN based methods and classification future, augmentation multimodality DNNs and hybrid approaches, weak supervised learning strategies and encoder and decoder architectures. So we have gone through this and we have decided this is the best way to present, where this complete literature survey in this paper they have presented in this format. So methodology is, I'm very happy that we are using encoder and decoder here. The same paper, encoder and decoder. So you can see in the first image that it has been passed to the encoder and decoder, we use coarse SN and coarse mask, which has been generated with a coarse mask. Then the coarse mask is concatenated. Here you can see the C. So concatenated with the original image, and has been passed to the convolution networks, which has a mask CN, have a gap, and which has been classified. With the help of it gives a results of a CAM image. So then the CAM image is subjected to enhanced, given to the enhanced SN, where with the help of the original image, which encoder plays a very important role, and decoders and gives an enhanced mask. So this how the working principle in this paper, okay, or we can call it as a methodology of MBDCNN model. So I go with one more slide with the methodology. So architecture of mask CN. So you can see here architecture of mask CN, which is in a center. So here the input is an original image with a masked image. So which has been generated from the first part, encoder, decoder, coarse SN, and the mask, which has been generated. So it has been fed to a convolution network, which is a separable convolution layer. Okay, then exception. It's an exception network. It's an exception network where it has been generated with a fine CAM. Okay, coming to the architecture of enhanced SN, which is present in an enhanced SN in the upper part. So it has been, you can see here encoder and decoder working very, very well. It's with an example you can see here. So the original image has been multiplied by 0.5, you can say. So image is going to minimize, okay. Then image features can be extracted. Then convolution of 256 in 1x1. So we have used ReLU E layer. So that has been multiplied by 0.5. Here I am dividing by, multiplying by 2, enhancing. So this gives an decoder part, this gives an encoding part. So architecture of SN. So this is the data set where the author has been worked. So ISIC 2017. So which is consisting of number of images is 2750, where 2000 train and 150 are validation, 600 for testing. So where it has been 3 class. So melanoma, seborrheic, okay. The labels has been given in that data set. Segmentation, boundaries, classification, and diagnosis. So author has been added 1320 images for this. So which makes 3 once again: melanoma, seborrheic keratitis, nervous, and image level, and which are labeled one. Then we have one more data set, PH2 public data set, which is 200 images. Nervous, melanoma, only two classes in this, with expert manual tracing. So here is the exact expert manual tracing has been done. So these two data sets can be available in the below website what I have mentioned. So you can download the website, download the data set from this websites. So coming to the next one, these are the results. So data sets. So as I said, they have used 2 data sets. One is ISIC 2017 and PH2. So they have used with segmentation and classification. So what they have used, the JA is nothing but a Jacquard indexing, and DI is a dice coefficient. Pixel accuracy and pixel SE is nothing but pixel sensitivity, and pixel SP is nothing but pixel specificity. So the same thing, accuracy here, specificity So, okay, sensitivity and AUC. So, the method, you can see that the method 1, method 2, the results you can see it over there, which has been mentioned, which method has been taken from which paper, we have mentioned in the bottom. So, method 1 and method 2, so ours is nothing but the present, the paper author. So, not ours, it's a paper author. So, the paper author is claiming with the same, so is getting a very good results when we compare to segmentation and classification methods. So, PH2 the same thing, the method 1 and method 2. You can see here in a pixel SP, the specificity, especially the method 2 claiming 95.3% more than the 94.6, which is negligible. Let's assume that. So, the only one concept, it's okay for us now. So, coming to the next one, the results, very important. So, the input image is there. So, course SN, the output image, the original encoding and decoding of this thing, localization of the map. So, what we want to do, when we combine with the input and the localization of the map, we get an enhanced SN. So, enhanced SN is compared with the ground truth. Ground truth is nothing but annotated thing by hand. So, when we compare these two things, especially, you can easily observe that. So, almost similar. So, when we come to the conclusion part, they proposed an MB DCNN model for a simultaneous skin lesion segmentation and classification, which consists of a classification network, mass CN, and 2 segmentation networks, coarse SN and enhanced SN. So, this model has been compared with the 2 data sets, as we know, and the results are acceptable. Since it has been published in IEEE 10 point more than impact factor. So, in the future work, they have mentioned that they have extended the proposed MB-DCNN model to an end-to-end learning framework such that it can optimize the segmentation and classification networks jointly and iteratively, aiming to specify the training process and improve the discrimination power of learning features. So, further improvement with the accuracy, performance and efficiency and proposed frameworks. So, by this I will end my presentation. Thank you and all.
Priya.
So this presentation provides a review about the paper, CKD network for skin lesion diagnosis and segmentation. So skin cancer is one of the most common cancer worldwide. Over 5 million new cases reported annually, underscoring its significant impact. So early detection dramatically improves the survival rate of several types of melanoma, evaluating it from 40% over 99%. And computer-aided task focuses on classifications and segmentation with a predicting a lesion type and automatically detecting and lesion boundaries. So the objective of this paper is to enhance the skin lesion diagnosis through accurate classification and segmentation using a flexible architecture that can be adapted according to desired requirements. Flexible architecture is essential due to the cost-intensive annotations required by recent multitasking learning methods in skin lesion analysis. Single task driven models exhibit limitations in fully leveraging available knowledge. So proposed solution, introducing a CKD network that optimally utilizes knowledge from different tasks for improved classification and segmentation simultaneously. So the proposed architecture in this paper contain different components. One of the component is core level segmentation, which is the initial stage that focuses on border lesion segmentation. A core segmentation mean that it have a larger blocks covering each class without much detail. A classification, and this identifying a disease related region using a entangled CLS model, classification module. So the next component is fine level segmentation, which is refining segmentation using a cascade context knowledge with the entangled segmentation module. Fine segmentation have a much high level of details which can given more down to a pixel level. So designed to feature entangled module, and one is entangled classification and another is segmentation module. So this classification module aggregates feature from initial segmentation to guide attention for disease related region in classification, and this module gathers relevant information or features that is identified during our initial segmentation step and combine them to enhance the subsequent classification task. So entangled segmentation, this integrates cascade context knowledge from classification to enhance the fine level segmentation, especially at uncertain boundaries. So this developed network provides an adaptive knowledge control. In other words, the modules in the network automatically adjust to the distribution of information between tasks, removing the necessity for researchers to fine-tune or experimentally determine the weight assigned to each task. The evaluation and comparison were done on the dataset AICTE 2017 and AICTE 2018 challenge dataset, and outperform a state-of-art method without restoring to ensemble approaches or external datasets. Effectiveness confirmation, the effectiveness or performance of the proposed method have been illustrated through interpretable results using a class activation map, CAM, and TNSC projection and classification segmentation outcomes. So this innovative approach addresses the challenge in skin lesion analysis, providing a robust solution for early detection and diagnosis of skin cancer. So this gives a dataset description that, about this AICTE 2017, and this dataset range are given here, and the number of training samples is 2000 with validation samples 150 and the testing sample is 600. Number of classes that are distinguished in this dataset are provided here, and the properties and training datasets are given with the testing dataset. The description about the dataset AICTE 2018 is given here. So methodology, this is the entire design of the proposed architecture, and the architecture has 3 components and 3 blocks, where the first block have core segmentation, and second block will provide a classification for the input data, and the third block will segment the images for the input data. So core level segmentation, named a root segnet, initiates with attention to lesion region of interest. So entangled classification and entangled segmentation facilitates the transfer of contextual information from the initial segmentation network, root segnet, to the classification network, CKD classnet. So entangled segmentation facilitates a transfer of knowledge from classification network, CKD classnet, to fine level segmentation network, CKD segnet. The backbone used for this network is ResNet 101, as the entire CKD architecture has been provided with this ResNet 101 as a backbone. This is adaptable to different backbone architecture, allowing flexible in model configuration. So hence, this CKD classnet enhances channel attention for improving semantic feature representation during the classification task. Experimental results on AICTE 2017 diagnosis test data set for CKD net and top rated SOTA methods. So from this table, it is seen that the CKD net have been performing better compared with all other models in the literature. So results on AICTE 2018 diagnosis test data set for CKD net and SOTA methods, which were trained from the scratch, and still it provides a better performance compared with other architectures. A performance comparison of the proposed CKD net with some SOTA method on AICTE 2017 segmentation test dataset is given in this table. Performance comparison of the proposed CKD net and some SOTA methods which were trained from scratch on the AICTE 2018 skin lesion segmentation dataset is given here. Segmentation results with the contour on AICTE 2017 test data set is provided, and the classes represent melanoma, SBK and NEV with the ground truth, and the contour segmentation is provided here. Class activation map visualizes it highlights the region of image that are important for particular class prediction. So the use of this SCAM helps interpreting where the model focuses its attention during classification. Visualizing the SCAM for 3 classification model. The FutureBug develops an end-to-end platform for clinical research, streamline the training procedure to reduce complexity, generalize CKD net, and knowledge diffusion strategy to diverse image classification and segmentation data sets. Thank you.
Thank you, participants, for this very informative presentation. Those who have not given their attendance, kindly scan the QR code now, and after that we can proceed to the computer lab for the practical hands-on session.